可以講少。Okay, testing. Ladies and gentlemen, the 8th International Conference on International Production and Construction ITC and the 8th International Conference on Construction Engineering and Project Management. 聽唔聽到頭先講一段？有啊，有聽到啊。咁而家係咪 online？ 跟住你講。我叫你讀 info， 跟住你講先。
Good morning and good evening to colleagues from all over the world. I wish to welcome you all to the joint IPC and ICC EPM Conference 2020. The Hong Kong University of Science and Technology is indeed very honored and privileged to be a co-organizer. It is particularly exciting to know that this joint conference has invited prominent speakers from around the world to share their valuable insights on their opportunities and applications of ICT, digital twinning, digital construction, BIM, etc. This is the best time for civil engineering in Hong Kong and the region, as infrastructure development is growing at a fast pace, and the need for sustainable development has never been more urgent. At this crossroad between development and sustainability, together with the emergence of new technologies, new understanding, and powerful analytical tools in various disciplines of civil engineering, and new ways for conserving and preserving the environment. Indeed, this is an exciting time for both practicing engineers and researchers in shaping our future smart cities. At the Hong Kong University of Science and Technology, we recently established the Great Smart Cities Institute, which has become a platform to bring together experts and professionals from a broad range of disciplines and institutional backgrounds, leading to the creation of tremendous opportunities for collaborative research and tech transfer activities. The Great Smart Cities Institute focuses on advancing 5 great attributes of smart cities development, namely green, resilient, empowering, adaptable, and transformative, or GREAT. To spearhead this effort, HKUST has set aside a budget of 50 million Hong Kong dollars in recent few years to make our campus smart and sustainable, and as a living lab to showcase what it is like to work and live in a smart and sustainable community. The objective of this initiative are to serve as a living lab for homegrown technologies and innovations, to inspire teaching and learning, and to cultivate partnerships with government and industries. And through this collective effort, make HKUST a global center of excellence for great smart cities research and education, and Hong Kong an exemplary great smart city. I see lots of connections between this joint IPC and ICC EPM conference and our Great Smart City Institute. While I welcome you to this conference, I look forward to foster closer working relationships with you to promote and establish collaborative research and development activities to make our cities great. Finally, let me once again extend my warmest welcome to all the participants, especially those from outside Hong Kong. I wish you a very fruitful and rewarding conference. Welcome to Hong Kong.
Good morning, distinguished guests and speakers. I'm very pleased to welcome you all to the 8th International Conference on Construction Engineering and Project Management. This conference was originally scheduled in December 2019, but due to unexpected social events in Hong Kong and the outbreak of COVID-19, the conference has been postponed. And finally, the organizing committee has decided to run the conference in an online mode, joining with IPC 2020 that is organized by our sister university, Hong Kong UST. I would like to take this opportunity to thank the members of organizing committee in both ICCEPM and IPC who have been dedicated to organizing this conference over 2 years. Also, we greatly thank honorable keynote speakers and paper authors for your continuous support and understanding during repeated postponements of the conference. I would like to express my sincere appreciation to all of you who generously helped to make this event come true and to become a success. The ICCEPM, established by Korea Institute of Construction Engineering and Management in 2005, has held biannually since 2015, aiming to bring together researchers and professionals in the world construction industry and to share relevant information and knowledge for the development of the construction engineering and management sector. As a hosting organization, it is indeed an honor to hold the 8th conference at the Hong Kong Polytechnic University. The theme of this conference is towards sustainable and smart construction. Sub-themes include, but not limited to, BIM and digital construction, automation and robotics, project management, integrated digital delivery, data modeling and analysis, and prefabrication. A glance through the list of presentations planned for the next 2 days reveals the amazing diversity of these topics. I strongly believe that this conference will provide valuable opportunities for us to share and discuss new ideas, concepts, and methods on these topics. Let me now close by wishing you a delightful and stimulating and fruitful conference. Enjoy.
Ladies and gentlemen, dear colleagues, as the founder of IPC, I'm very pleased to welcome you to the 8th International Conference of Innovative Production and Construction, IPC. It is high time that such an event took place to highlight the remarkable contribution which IT applications make in so many areas of our production and construction industries. I would like to acknowledge the conference chairs, Professor Jack Chen, Professor Henley, and Head of Department, Professor Liu in Hong Kong UST, and Professor Albert Chen in Hong Kong Polytechnic University for their fantastic work and efforts put in the conference. Taking slightly different angles of welcoming you, I would like to walk you through the history of IPC and its development over years. As you know, a key role of IPC is to bring together production and AEC researchers and practitioners from Australasia and the rest of the world, sharing the latest innovation in the areas of smart building and construction. Originally started from Australasia, IPC was initiated in 2012, which was pretty much the same year as the Beam Center at Curtin University was established. And IPC has been held in different cities since then and has surpassed the various challenges that our industry and education system has faced over the years and has adapted to changing technological trends in the industry. From having the conference of just about 50 participants back in 2012, we have come a long way in making the conference a huge success, with now about 300 delegates from all around the world. Every year, we have a theme for this conference ranging from technology to business. And this year, the theme is towards advancements in technologies and process for smart building and construction. But this year, this conference holds special value because this is the first conference in its history. The entire conference is taking place in digital platform. And I thank you, everybody of you, for joining us. I would like to conclude my speech by encouraging the delegates to participate with an increasing number in all the activities and discussions through the digital platforms over the next 2 days. I really wish every one of you a very successful, safe, and fruitful conference. Thank you very much.
Morning, ladies and gentlemen. Good afternoon or good evening, depending on wherever you are. This is Young-Soo Jung on behalf of KICEM, which is an academic society here in Korea, Korea Institute of Construction Engineering and Management. I'm very honored and very glad to welcome all of you to the ICCPM online conference. First of all, I would like to express my sincere thanks to the conference chairs, Professor Heng Lee, Professor Jun-Oh Seok, Professor Hung-Lin Chi, and Professor Albert Chen, Professor Geoffrey Shen of the Hong Kong Polytechnical University, and also thanks to Professor Adeli of the Ohio State University. As everyone understands, due to the unexpected circumstances, the organizing committee has gone through a really difficult and challenging process over the last 2 years to make this wonderful and successful conference happen. ICCEPM, International Conference on Construction Engineering and Project Management, started our first meeting back in 2005. And this is our 8th meeting. Over the past 15 years, the ICCPM has been continuously growing in terms of the number of participant organizations, as well as the number of participating nations. As you know, the business environment and the new concepts and new emerging technologies are rapidly ever-changing every day. And international cooperation is now an everyday occasion for researchers as well as the practitioners. Therefore, having the places where we can get together, just like today's conference, is getting more and more important. Basically, ICCPM is geographically based in the Asian region. But ICCPM's primary mission is to promote genuine international collaboration with everybody from all around the world. I remember that it was in the previous meeting in Chengdu, China. We talked about extending the ICCPM activities in order to boost this international collaboration. It can include small group meetings, or possible joint research in between biannual conferences. We will have time to discuss about the plans and method about this issue. But under the current pandemic situation, we will start off with online meetings, and we will move forward step by step in the near future. We are very looking forward to everybody today here joining these upcoming ICCPM activities too. And I also really hope we can see each other in person pretty soon. Thank you again for the great effort made by the organizing committee. And I hope all of you enjoy the conference today and tomorrow. Thank you very much. 감사합니다.
Distinguished guests, ladies and gentlemen, on behalf of the organizing committee, I wish to extend a sincere welcome to ICCPM and IPC 2020. This joint conference has brought together leading researchers, practitioners, educators, and policymakers from all over the world. It is an excellent opportunity for us to discuss emerging issues of our field, to share the latest research outcomes, and to collectively decide the research agendas of the future. The pandemic has made it difficult for us to travel and meet physically. However, I can feel that our hearts are connected. I hope in the near future, the world will return to its norm, and we will be able to travel and meet each other again. I'm sure that we will have fruitful discussion and intellectual debates. I sincerely hope that you will enjoy the rest of the conference program. Meanwhile, let us stay safe and vigilant. Once again, thank you so much for your participation, and my best wishes to you and your family. Thank you.
Dear distinguished guests, keynote speakers, ladies and gentlemen, good morning. It is our great pleasure and privilege to welcome all of you to the 8th International Conference on Innovative Production and Construction, or in short, IPC 2020. The conference provides a platform for all of us from academia and industry to share our insights, experience, and brilliant ideas to improve the building and construction industry with the help of technologies. IPC is an annual academic conference exploring how technology could be effectively utilized in construction. For many years, the Hong Kong University of Science and Technology and its BEAM Lab have been organizing conferences in a similar area. We also collaborate with the Great Smart City Institute at Hong Kong University in many events. I'm very delighted to organize the IPC 2020 conference in parallel with the ICCPM 2020 conference organized by the Hong Kong Polytechnic University this time. We share common commitment to promote the latest technologies and development from innovative research activities in the areas of smart buildings and construction. We hope the conference can bring you many exciting technologies and ideas, which you will enjoy and benefit. The conference adopts a timely theme towards advancement in technologies and processes for smart buildings and construction. It is one of the ideal
pursued by the architecture and engineering profession for a long time to create a more sustainable and livable space so that the users of the building can get a sense of physical and psychological satisfaction. Smart buildings integrate architectural design and ICT to achieve a green, healthy, comfortable living environment for all of us. And smart construction is also exciting and important for our built environment. Technology has virtually penetrated all areas of design, construction, and operations of our AECO industry. To effectively benefit from technology application, it is essential that we professionals get ourselves ready for transforming our practices and keep identifying smart ways for digital transformation. I'm glad that IPC 2020, together with ICC PM 2020, will have over 15 keynote presentations and about 100 technical paper presentations in this two-day event. I would like to take this opportunity to sincerely thank the local organizing committee, especially Connie, Kelly, Momita, and Wei Wei, and the International Scientific Committee for their hard work behind the scene. I would also like to thank all of you for joining us and sharing your valuable experience and ideas. This year is a very special year. This conference has been kept postponing due to social issues in Hong Kong and then COVID-19. I'm very glad that the IPC 2020 conference can be held finally in online mode. Thank you all very much for your support, which makes this conference possible. Finally, as the conference chair of IPC 2020, I hope you will enjoy the rest of the conference and find the conference fruitful these 2 days. Thank you very much once again and wish you all very best.
So do you think we are delighted to have Professor Buju Akesi to give a presentation on the topic of context-aware AI for construction and facility infrastructure management. Professor Buju Akesi is the Paul Crescent Professor of Civil and Environmental Engineering, Associate Dean for Research for the College of Engineering, Director of the Engineering Research Accelerator, and Co-Director of Pennsylvania Smart Infrastructure Incubator at Carnegie Mellon University. She obtained her bachelor's degree in civil engineering from Middle East Technical University and her MBA from Bentley University of Ankara, Turkey. After that, he obtained her master and PhD degree in civil and environmental engineering with a specialization in construction engineering and management from Stanford University. Professor Akesi has over 16 referred journal publications and 18 referred conference publications. Let's welcome Professor Akesi, please.
Thank you. Thank you. Thanks for the introduction. Let me share my screen. Just 1 second. Oops. Now it. Okay. You can see my screen, right? I assume you do. So thank you very much for the introduction, and thank you, Professor Jack Chan and the organizers of the IPC and ICC PM conference for inviting me as a speaker. I was hoping to be there in person and in your beautiful country, but given the circumstances, this is how we're gonna do this. And I'm still very excited to talk about our research on context-aware AI for infrastructure and facility management. So I always, this is, if you have seen me talking before, I more or less talk about the same thing at the beginning of my slides, because I'm still baffled by the fact that some of the seemingly easy questions are sometimes it's difficult for our civil engineers and project managers to answer, given the given the fact that we have complex buildings and distributed data sources, and hence they don't always have the situational awareness that they need to be able to answer the questions like, are there any deviations at my job site? Where is the valve to shut off the water? Or how well is my HVAC system performing? Not being able to answer these correct questions effectively results in quite a bit of waste, and I gave some examples of waste that are generated because of that. But ideally, we need to move from just being able to answer these traditional asset management questions to more proactive and predictive decision making, right? So we need to move away from reactive to proactive and predictive decision making. We need to move away from doing subjective assessments to more objective assessment. We need to move from making decisions with limited information to complete situation awareness. And we need to move from treating our systems as a single system, but think it as more interacting physical social systems. And in an ideal world, we need to do these autonomously, right? So that's where the holy grail of everything is. When we think about autonomous, we typically, the first thing that comes into mind is autonomous cars, right? So when we think about a car, we see that a medium-sized sedan has 400 sensors on it. So it's a giant computer. And we treat that car as a giant computer through some intelligent diagnostic tools. And hence, nowadays the autonomous cars are here, right? So that the driver is in a much more passive role and can do other things while driving. When we look at our buildings have a lot of sensors too. So a 60,000 square foot building has 21,000 data points that can be, that sends out data on an every minute basis. So it's a giant computer on its own too. But when we start treating our buildings, we typically still treat it as not as a computer, but we go back and try to fix this giant computer with hammer and other things, right? So the manual diagnosis and maintenance is what we do. And autonomous buildings are not quite there yet. And this little problem here is actually costs us not being able to manage our HVAC systems effectively. It has a lot of energy waste implications. And when we think about the world's energy usage, a portion of it is wasted because we're not able to effectively detect and diagnose faults in buildings. So one might say, why aren't the buildings there, right? The cars are there in terms of autonomy, but the buildings are not there. And there are several reasons for it. So we have each building is being very unique. And when we think about each building and the building systems in it, it creates a lot of complex control logic implementations to manage these interdependent building systems. And each component in the same building might end up behaving very differently based on the context of the usage. On top of that, we do a lot of changes to our buildings, right? The usage, the layout changes occur throughout the building's life cycle. And this is basically changing your sedan to an SUV to back to a van and back to a sedan again, if we were to do it in a car. And then owners and the users are deeply involved with buildings, and in cars, that's not the case. So these all create challenges where we can't truly apply off-the-shelf AI and other techniques to turn our buildings into autonomous buildings. So hence, we need to bring the context into the decision making, which means that we need to bring a bunch of different data sources. When we think about the data sources, we do have building information models where it depicts, in a semantically rich way what we expect in these facilities. We also have sensors either embedded in our building automation systems, or we can take them out to the job site like laser scanners, and within minutes we have gigabytes of data about what is happening geometrically at the job site. So these are all very complementary data sources that help us build a contextual knowledge to be able to start implementing some interesting algorithms. So in our research, we have been working on integrating sensors with BIM to support this contextual AI. So with it, the BIM provides context to the data that is collected in the field, and the data in the field provides reality to our building information models. So it's always updated and a good data source that you can build on. So, we used to call this living information model. Nowadays, the term for it is digital twin, where there's a virtual representation of the facility and its behavior, where you can then utilize that data to do some interesting analysis. So over the years, we have been asking several research questions. One is, how do we create these digital twins of these facilities that reflect the as-is conditions? And that brings, the reality capture to digital models, or approaches that require updating of the existing digital models. The other aspect is that our buildings are so complex that we need to be able to integrate a large heterogeneous data sources to enable the situation awareness. And how do we do that is still a research question. And then finally, how do we derive actionable information so that we get into more prescriptive and predictive maintenance rather than reactive or corrective maintenance? So I'll give you some of the examples of research that we did in relation to the first and the third question. So when we think about how do we create digital twins of facilities to reflect the as-is conditions, there are different data sources you can use to do that. You can take the laser scanner and then you need to turn the points to BIM, or you can do the images to BIM, or you can do the drawings. You can analyze the drawings and turn the symbols to BIM. Each of these provides opportunities and challenges associated with it. So when we think about points to BIM, there's a whole computer vision research that goes in computer science and robotics, as well as civil engineering. And many of the algorithms that are developed in CS and robotics typically assume that the space are clean and simple. It assumes that the algorithms assume that there are a lot of unique features in the space, so we can identify things according to those unique features. And their goal in that case is to be able to generate a geometric model, not necessarily bringing a whole lot of semantic understanding associated with it. In reality, in our case, right, so we deal with very cluttered spaces. We don't have a lot of unique features, which makes it very challenging to use only data-driven solutions. And we want to understand the complete scene understanding rather than just creating the geometric model. So this creates a challenge that we can't really utilize purely data-driven solutions, purely deep learning-driven solutions. So what we have done is to combine those deep learning approaches together with the contextual information, where the context now comes from the domain, the civil engineering domain, where it defines, some kind of directional consistency or vertical ordering and contains relationships, and apply those to the data-driven approaches that are implemented that identifies these semantics. And with that, we were able to identify, build up the semantics much more reliably than if we were to use purely data-driven solutions. When we look at the images, it's a similar problem too. So what you're seeing on the top left is a bunch of images randomly collected at the job site for many different reasons. As you can see, there's no overlap. There is a lot of repetitive scenes, and it's not clear which part of the building that these scenes belong to. And then we also at job sites, there's a dynamic scene, right? The construction evolves over time, and the same wall look very different early in the construction versus later in the construction. So these also create challenge in figuring out where these pictures are taken, so that we can analyze the picture and assess what's happening at the job site. So we tried, again, most of the vision-based approaches uses pixel-based and not necessarily semantic ways to reconstruct the scene. In our approach, we actually did it a little bit different, and we are using first understanding the components in each picture and use that as a way to figure out where this picture might have been taken within the BIM, and then localize it and do the analysis accordingly. Again, this is a different type of an AI approach. It's not a purely data-driven. It brings the context, the domain knowledge together with the data to be able to do the analysis. And then finally, okay, so we have a digital twin, and what are we going to do with it, right? So the goal is to turn that digital twin to an actionable information. And I gave you the example of these HVAC fault detection and diagnosis, turning out to be a pretty challenging task for us in our industry. And you might ask why that's the case. Here's a typical fault that occurs in the HVAC system that nobody could identify because there is no symptom, right? So there's no problem with on the occupancy side. What you're seeing is a supply fan on the left when the damper is 100% open, it has a certain speed of 37%, and it generates a certain airflow. When the damper gets stuck, right, the HVAC system starts having a fault, damper being stuck, all of a sudden the supply fan works much harder. The speed is 92%, but it still generates the same airflow. So at the end, there's no problem for the occupant. The occupant doesn't feel anything, so there's no complaint. As a result, there's no need to detect a fault. But in the meantime, we're wasting, twice as much of energy usage than we were if the system was operating efficiently, right? So that's a challenge, and this is a very difficult thing to solve if you do a purely data-driven solution, because you don't know, how these dampers and supply fans impact each other. On top of that, we do have in a single, air handling unit, this is all the different, relationships that exist in the control logic that defines the behavior of that air handling unit. So as you might imagine, it's very difficult to manually track these and to be able to identify faults even in a single air handling unit. So that makes it challenging because these systems are very, very complex. And then finally, each of these systems actually behave differently in different parts of the building. So what you're seeing is 6 different rooftop units. And we did a training on one rooftop unit. And when we tried to apply that training of fault detection to the other rooftop units, you see that the performance kind of degraded really fast. So again, which suggests that you can't really learn from one unit and apply it to another because these units behave differently under different contexts. You still need to bring the context, which means that many different data sources, manuals, pictures, drawings, control logic, all needs to come together to make this happen, to provide the context for the systems and hence to be able to run a bunch of algorithms. So here, just for full disclosure perspective, so this was the research that we did at Carnegie Mellon, but we also did a spin-off out of this, and hence that's why I'm putting, both logos at the same time. So once you have all this data integrated, now you can contextualize where the faults are. You can see it in the model. You can also do root cause analysis and actually tell what the problem is, right? So incorrect cooling control. and then calculate the energy efficiency impact of it. And then if the user doesn't wants to see what's happening behind, you can take the user behind the scenes and tell you where the diagnosis has occurred, where the fault occurred in the raw data. So you're hearing from, when you talk about AI, a lot of people say that it's black box, it's not explainable. But what you can see here is that when you combine it with the domain knowledge, you can actually explain what is happening behind the scenes. So this implementation alone results in about 30% HVAC energy savings in 1 month of deployment. So we're not alone who says that domain knowledge is important. In fact, computer scientists also realized the fact that we can't do it just purely data-driven. And this is from DARPA, I think about 1.5 years ago. Maybe 2 years ago. I'm kind of lost track since the pandemic, but that just puts saying that we can't. Second wave of AI was all data-driven solutions, but the third wave of AI actually brings the domain back at the crux of the algorithms, because that's the only way that you can generalize what you're doing and explain what you're doing, right? So that's we're not alone in saying this. So just to finish it up, I want to highlight that we are also working on a project that applies to all the things that I've talked to habitats in Moon and Mars, smart habitats. And I want to put a little pitch up there saying that we are looking for PhD students and postdocs to work on this project. So if you're interested, please do reach out. Thank you for your attention. And I guess I'll look at the chat to answer my questions, and I'll finish with my acknowledgements of my students who are the brains behind the things that I presented. So with that, I think I'm going to stop sharing and look at the chat. Is that correct?
Okay. Thank you, Professor, for your very nice presentation. May I also invite our moderator, Professor Heng Li, conference chair of ICC EPM, for holding the Q&A session for us. Professor Li and Professor Akisi, please.
Okay. Can you hear me?
Yes, I can.
Yeah. Professor Akinci, thank you so much for your information-rich and thought-provoking presentation. We all follow your work and we all admire your work. And for many reasons, actually, I have a very good friend, Pimpo Tan. He actually got the same master's degree from Tongji University. He was a much better and a younger version of me, actually. Yeah, we also do a lot of work in digital smart construction, but your idea of autonomous building is very new and attractive. Personally, I wish to explore opportunities, work with you and Pimpo a lot more. Okay. Having said that,
anytime you're welcome. Just reach out.
Okay. Thank you. Now the floor is open. I guess there will be lots of questions from the audience.
Okay.
How do they raise questions? Oh, okay. Yeah. Okay. If but the audience are waiting for, they are thinking about how to raise questions. I have actually a question. You said that the third wave of AI is coming into our industry. We are actually working, because in our part of the world, we are working at the new buildings, new construction. Do you have any advice on how to apply AI in the new construction project?
Well, new construction projects are in certain ways easier, right? Because you you design the data collection as you are building it, versus the old buildings. It's much more challenging to generate the data that you can utilize for AI. So, new buildings are much more, I guess, much more fruitful ground to apply the AI. Somebody actually, when we use this, utilize the Lean FM's system in a couple of the new buildings, A lot of people ask, well, there's no way that you can find any faults because those are new buildings. But to our surprise, to my surprise too, these building systems generate faults almost from day one, even if you do commissioning. We have tested in several buildings that have the commissioning, and still there were faults in the building. So there's still opportunity for improvement even in the new buildings. So in terms of new buildings, it's great. You have the data in place, and you still can make an impact from the get-go because there are still errors in the buildings that are newly operational.
Yeah, I totally agree with you. Big data driven approach is going to change our industry. Starting from design to construction to until asset management. Again, is there any questions? I guess your presentation is so comprehensive. Everyone, is fully, appreciated. In that case, let me, represent the whole conference organizing committee to sincerely thank you for your great contribution. Thank you so much. Thank you.
You're welcome, and hopefully next time we'll get to see each other rather than Zoom.
I actually, my supervisor, Manu Maya, got a PhD from Carnegie Mellon.
Yes,
I never had the chance to visit Carnegie Mellon. Maybe I should pay a visit to you. And
as soon as we're over this, please come and visit us.
I will. I definitely will. I like a ping ball, so pass my best regards to him. Yeah.
I will. Sounds
He's doing so well. Yeah. Thank you so much.
Awesome.
Thank you.
Okay. Thank you.
Thank you.
Thanks.
Okay.
Bye.
Goodbye now.
Bye.
Okay. Thank you, Professor Akiti and Professor Lee. Next, we are delighted to have Professor Jim Anuba to give a presentation on the topic of the role of analytical systems and digital in construction industry 4.0. Professor Jimmy Anuba is a professor and the dean of the College of Design, Construction, and Planning at the University of Florida. He is a fellow of the Royal Academy of Engineering, the United Kingdom National Academy of Engineering. He has over 500 scientific publications, and his work has received awards worth over $150 million from awarded authors. Let's welcome Professor Anuba, please.
Hello. Good morning, and thank you very much for inviting me. It's a real pleasure to be here. Obviously, I would have preferred to be there in person, but we'll have to do it this way. So thanks very much for inviting me. I'll just share some of the work that we've been doing on the role of cyber-physical systems and digital twins in industry. First, a little word from my university. The University of Florida is currently ranked 6th in public research universities in the US. And we just have had a very recent investment in AI, a $100 million investment in partnership with NVIDIA, which will provide us with the very best and fastest AI supercomputer in US higher education. So very shortly, we'll be advertising for a number of new faculty in that area. So in terms of my presentation, I'll start with the outline. I'll provide a bit of an introduction, talk about cyber-physical systems and digital twins, and then talk about some of the lessons we have learned and potential future direction, and then summarize. So the context for construction 4.0 is really this move towards industry 4.0, which is really the fourth industrial revolution. And it's also situated within the context of continued technological advances and the evolution of working practices within the industry. So what I plan to do is to briefly explore Industry 4.0 and then look at the implications for Construction 4.0. So currently the focus on Industry 4.0 is really on cyber-physical systems, and industrial revolutions 1 to 3 have resulted in huge paradigm shifts going from mechanization and steam power to mass production, computing and automation, and now focusing more on cyber-physical systems and associated technologies. So the expectation is that Industrial Revolution 4.0 will do the same in terms of resulting in significant paradigm shifts. So the key elements of that are really that this originated from manufacturing. It does encompass topics such as CPS, IoT, cloud computing, cognitive computing, with the key principles of interconnections between machine devices, sensors, people, but then also elements of information transparency, which is needed for big data analytics, and then technical assistance both to humans and other systems. And as part of that is this notion of decentralized decisions, autonomous and automated decision making. And Dr. Akinci talked a little bit about autonomy as part of what the goal should be for us. Cybersecurity is one of the major concerns associated with this move, and there are a number of other concerns as well. So the implications for Construction 4.0 are really that we need to look at mechanisms for capturing and managing large volumes of data. We also need to look at support for greater collaborative working, proactive leveraging of emerging technologies, new business models, both at organization and project organization levels, as well as cultural changes with regard to technology adoption, new ways of working, amongst other things. And so this, our industry does need to invest in some of these enabling technologies, particularly with regard to CPS and digital twins, which is the focus of my presentation. So what exactly do we mean by CPS? I'll talk a little bit about that, and then I'll talk about some prototype applications that we have been working on. So essentially, we're looking at the tight integration of the physical environment with the cyber environment. And there are a number of different definitions. In terms of the built environment, the main application areas have been in structural health monitoring, but then also in building energy management systems, increasingly in construction engineering and management, as well as transportation systems. So most of our work has focused more on the construction engineering management aspect. The key elements of this is really being able to create a mechanism for bidirectional coordination between a virtual model and the physical construction. And there are a number of enabling technologies that are required in order to be able to do this effectively. I should say that you do not need all of these at the same time to be able to do this. You can use any subset of these that allow you to have that bidirectional coordination. And then why do we really need this bidirectional coordination? There are a number of things that can change during a project, either from the design side or from the construction side. Also being able to track progress from the virtual model, manage a number of constructability issues, and then improving tracking and management of assets, and in some cases, being able to control components and subsystems in the build facility. So I'll give you some examples of the CPS applications that we have worked on. One of the first that we did focused on component tracking and management. This dates back to about 10 years ago when we started working on this. Came up with a system architecture that allowed us to develop the applications. And then we also looked at a number of deployment scenarios. And this really spoke to what sort of problems we are trying to address. In this first example, we're looking at steel placement, being able to deal with issues associated with design changes and constructability. And then we also looked at design changes in retrofit projects and how that can be automatically communicated between the virtual model and the construction site. And the third scenario related to light fixture tracking and control, where we were able to bind the physical light fixtures with the virtual representations such that you could actually manipulate the light fixtures from the virtual model. So these are the deployment scenarios that we looked at. And in terms of actual implementation, we focused mainly on the light fixtures example scenario and the component placement, looking at being able to track the placement of doors, windows, and roof of a simple mock-up facility. And this allowed us to do some automated component placement tracking so that if you move things in the physical environment, you actually could detect that those were also being moved in the virtual environment. And then we moved on to work on temporary structures. And the main reason for this is that temporary structures are recognized as having significant impact on safety on construction site. And we decided to use scaffolding as an example in this particular case. One, because it was associated with a lot of safety issues, but then also the principles we come up with regard to scaffolds could be applied to other types of temporary structures. And so again, we did a physical laboratory mock-up and had a virtual model that we created. And we're able to then play around with this such that any movements in the physical structure could be tracked in the virtual model. And we could then identify, for example, the absence of braces, the settlement of supports, the overstressing of specific components, and then we could alert the appropriate site personnel while also being able to view what was happening in the virtual model. And so this just shows you what happens and the sort of alerts that are issued in the dialog box there. We also developed a simple app that's based on the phone, on a smartphone, that the safety manager or an appropriate person could utilize in real time to track what is happening with this particular temporary structure. And then the third application that we looked at was associated with mobile crane safety and efficiency. This came about because over the years, there have been a number of critical safety issues with mobile cranes on sites, in some cases with fatalities. And the main issues that were the most serious issues related to stability and overturning of some of these cranes, as you can see in the picture to the right on the screen. Also, there are a number of issues with collisions, falling objects from cranes or the cranes striking people or vehicles. And so we thought that we could apply CPS to this problem. And we had a project funded by the National Science Foundation that was in partnership with my colleagues at the University of Illinois and also at Penn State, from where I moved to Florida. So we worked with a number of industrial collaborators, including the Association of Equipment Manufacturers and some crane manufacturers such as Manitowoc, and then a number of construction companies. And the number has grown, but these were the original partners in the project. And what we were focusing on was how to capture the context of the crane operations through integrated planning, sensing, and equipment data, and then being able to create a CPS system that had virtual construction site models, a means for assessing the stability of the crane, sensing, actuation, and control modules that would allow us to improve the safety and predictability of the operations, as well as being able to provide cyber-physical feedback to the operator for control purposes. So we're monitoring a whole series of things associated with the mobile crane operations. And so some of the elements that we looked at included reviewing crane accident records, just to establish mainly what are the primary accident areas, causes of accidents, and what were the critical safety issues in those situations. And then also developing a taxonomy for mobile cranes so that we could understand which particular cranes were being used on any particular site. And we did have colleagues at Illinois developing algorithms that would allow for automatic mobile crane recognition using UAVs on site. And then based on that, we could feed that into the planning. Also doing site layout modeling so we could plan crane lifts and safety analysis. And then we also undertook failure mode effects analysis to establish critical failure modes and key hazardous situations. And then based on that, we developed a safety integrated virtual simulation that would allow us in real time to track what is happening and provide feedback. We also looked at the mechanisms for providing feedback to the crane operator in what we call the transparent cockpit. And then we also looked at computer vision systems for tracking workers and other moving equipment in the vicinity of the crane operations. So all of that went into the design of the system. And this shows you the system architecture that we used that allowed us to track a variety of things at various stages of the process. And so at the core of this was this bidirectional CPS system, which on the left-hand side, we have the virtual model where we developed a model of the site and the crane. And then on the right-hand side, you actually had the physical site and the physical crane from which we try to capture critical physical elements using appropriate sensors. And then, so the site environment data, we obviously used a number of different tools to capture what was physically happening on site. And then with regard to the crane itself, we were able to capture elements of the crane itself, as well as its movement and its contact state with the ground. And then, so this is the simulation model. And because of bandwidth issues, I've chosen not to run the video, but this actually shows you the view from the crane operator. And then on the left-hand side, you have the virtual simulation model. And then what we then did was to integrate into this the most appropriate safety rules that related to the crane operations. And so one of the elements that we looked at was potential for collisions. And in doing this, we looked at OSHA rules and regulations to define what the appropriate clearances were, and then being able to, as you can see in the cockpit, provide feedback to the operator as to what issues were problematic. And then also we did analysis of overloading issues that could be associated with the crane operations as well. So these are just other examples. One of the areas we looked at also related to the capacity of the crane to tip over. And we're able to track that and make sure that appropriate alerts were issued to the operator as appropriate. So following on from the work that we've done on cyber physical systems, we started to take a look at digital twins. I think, again, digital twins have already been mentioned, and you will hear a little bit more because there are a number of other keynote speakers that will talk about digital twins. But essentially, we are talking about an integrated multi-physics, multi-scale probabilistic simulation of a complex product, which uses the best available physical models, sensor updates to mirror the life of its corresponding twin. And the critical elements are having the physical product and the virtual model, and then being able to integrate them, having connections of data and information. And so you collect data from the physical environment using sensors and a number of other data capture tools. And then you can send information to drive based on from the virtual model to drive physical processes as appropriate. And so you're able to reflect in real time what is actually happening. And then you can make adaptations and also run what if scenarios that give you a sense of what is actually happening and how you may want to change what is going on. So this actually originated in the 70s from the NASA's Apollo program. We have had a number of applications in manufacturing, as well as in industrial engineering and robotics. And now there's a lot of interest in applying this to the construction industry. And lots of different research groups as well as national groups are beginning to look at this. So one example is some of the work being done by our colleagues in the structural health monitoring area, looking at use of digital twins for structural health analysis. Also, there's been some work on looking at how to mirror the life of the physical entity in order to support decision making. And so there are a number of critical elements in this. How do you actually understand the real-time behavior of a system and then be able to provide information across its life cycle and then optimize the system behavior as you go along. So our particular focus initially has really been on how to apply this to what we've been doing with mobile crane safety. And so we've been able to do this sort of modeling where we have the physical side, and then we're also able to develop a digital twin of those processes. And then you can actually simulate the physical lifting operations. In this case, they're lifting precast concrete panels in place. And that shows you the simulation of that process. And so based on all of the stuff that we have done so far, looking at these elements, we have learned a number of lessons, and then that also has given us some insights as to potential future directions for both cyber physical systems and digital twins. One of the main lessons is the fact that you have to have a clear understanding of what the problem is that you are tackling, and then come up with an appropriate mechanism to ensure that that you are addressing the real problem. And in order to be able to do this effectively, you have to have accurate and up-to-date virtual models. Also, you need to have a pretty good design for this bidirectional coordination mechanism, because it's one of the most important aspects of the development of a cyber-physical system. And then you also need to look at the choice of appropriate sensors and sensor networks in order to communicate capture what is happening in the physical environment, and then be able to relay that to your virtual model. One of the things we found really useful was to undertake a number of laboratory scale experiments to help to prove the concept prior to trying to deploy this on real construction sites. And that helped us to iron out some of the critical problems in making sure that things work well in a controlled environment before looking at a site environment where you have a number of other considerations. And some of those really relate to issues of scalability, cost. There are also issues to do with power, and then the extent to which you can have most things wireless, so you don't have trailing wires getting in the way of site operations. And then there's also the fact that you have a lot of other moving parts on the site. So all of these are practical considerations that have to be taken into account. And in terms of future directions, I'm not brave enough to make any predictions as to where things will go. What I will say is that the future directions will be governed by what new construction applications we're able to dream up for CPS and DT. But then also we have ongoing technological development that will help to steer where we go in the future. So with regard to new construction applications, and I should say that some of these are not necessarily all that new, but there are areas that are beginning to gather a lot of momentum right now. For example, there's a lot more interest in deploying CPS and DT in facilities management. And for us, one area we've been looking at is healthcare facilities management. We've got a student working right now looking at how we can leverage these technologies to improve what is traditionally known as the environment of care, so that healthcare operations can go on without the facilities being a hindrance. With a lot of the interest in smart cities as well, there's tremendous opportunities to deploy CPS and digital twins, and a number of groups are beginning to look at these, and also looking at integrated infrastructure management and how CPS and digital twins can improve the understanding of how to manage these, particularly the interdependencies between the infrastructure systems, and then being able to capture some of that in real time. Also, district scale energy management, where you're moving away from individual buildings and looking at campus scale, district scale energy management, being able to develop digital twins of those and being able to manipulate those in real time to maximize the use of energy. And then Burchard talked about autonomous buildings, and I think that is really where we're headed. I think that in the more immediate term, we really need to be looking at what I would call self-aware and content-aware constructed facilities that have some understanding of what their role is and what they contain, and then being able to utilize that information in concert with other related facilities to actually carry out some automated or autonomous tasks. Increasingly, there's a lot of work going on in terms of resilience, and I know that Professor Dumpling Fong is going to be talking about this, but in looking at resilient built and natural environments, the critical element is how do you capture what is happening in both the natural environment and the built environment, and then have these to work synergistically to improve our operations. And in terms of technological development, there's a whole series of these. Again, Bruce talked about context awareness. We're all conversant with the use of drones on site, 3D printing, cloud computing, communication networks as we move into 5G and beyond. And then sensors will continue to be developed, and we are highly dependent on these as we, again, try to deploy CPS, DT, and also the Internet of Things on construction sites. We are now in a new wave of artificial intelligence, as we've already heard, and that provides tremendous capacity for improving our understanding and deployment of these technologies. So to wrap up, I would just say that there are a lot of benefits from CPS and DT. Obviously, the real-time information exchange is important. There's scope to reduce construction risks. We can have more accurate as-built models for operation, FMD construction, and other purposes. We also have increased capacity for what-if simulations that will help us to improve what is going on. And then improve opportunities for sustainable construction practices, improve safety, and then also improve proactive safety monitoring. And then again, if you're able to control processes in real time, then there's a whole lot you can do with controlling components in place. Finally, I think that the fourth industrial revolution will have a major impact. CPS and DT are key elements of this, and the construction industry will need to adapt or adopt these technologies to have for them to have an impact in construction. There are lots of applications in construction that are being developed, and I gave you a few examples. And throughout this conference, you'll also learn about a few more examples. There are considerable potential benefits. We have learned some lessons from what we have done so far. And with digital twins, there are additional opportunities, particularly in the area of what-if simulations. And future directions will certainly focus on new application areas and integrating emerging technologies. And I'll end on that note, and I'll have end with a plug for a new book on CPS in the built environment, which includes a number of authors that are also contributing to this conference. Thank you.
Thank you for a nice presentation. It's a very fruitful and comprehensive sharing for us. Before the Q&A session, I would like to tell our audience how to use the Q&A function. The Q&A tab is on the right-hand side of each session. Please mention speaker name ahead of the question. Our moderator will choose among the questions, repeat them loudest for all audience, and ask the speaker's response in short answers after his or her presentation. Please feel free to share your thoughts or raise your questions. Now, may I also invite our moderator, Professor Heng Li, for holding the Q&A session for us. Professor Li and Professor Anuba, please.
Thank you, Professor Jimmy Anuba. Hi, Jimmy. Very good to see you again.
Hi.
You look
Good
so good. Yeah. You know, thank you for your great presentation. You know, We are always amazed by your capacity in getting big research grants and putting together, big research ideas. I mean, personally, while the audience are preparing questions, I have a question for you. I'm in the process of preparing a Hong Kong major research fund proposal. The background is related to digital twin and the cyber physical system. So my question is, what are the ground challenges in this area that deserves, scientific investigation? If I have to convince the funding body that it deserves to be funded. So I need your brain, your advice.
Well, yeah, that's not an easy question to answer, because I think that with grants, typically you're looking at in two different elements. One is what are the technical or technological advances that we can contribute? And then the second is what are the real problems that we will be addressing?
Right.
And I think typically you have to look at both of those, because it's been said that when you have a hammer, everything looks like a nail. So while we have the technological tools, we need to make sure that we're actually using them appropriately to address critical problems in industry and in society. I think for the construction industry generally, there are a number of critical issues relating to what I broadly call appropriate use of technology, and then appropriate access, capture and use of data. I think we do not adequately capture the critical data that we need to inform decision making in many situations. And so being able to capture those effectively and then leverage them to provide the appropriate context triggers that then inform decision making or then inform automated or autonomous systems is very important. And then some of the issues that we deal with obviously provide opportunities to then contribute to the science of CPS or the science of DT, because our problems are typically different from those in the manufacturing sector. And so being able to look at those, the uniqueness of the problem that we are solving, and then finding a way to feed that back to the fundamental science, and by coming up with new concepts and new insights, I think are the key elements.
Yes, thank you so much. That is very helpful. Let me be more specific. I'm thinking to pinpoint the difficulty in synchronizing the data exchange between the digital model and the reality using IoT or some other technology. Would that be a ground enough, the challenge ground enough to convince the funding body?
Yeah, I think that is a key problem, but I think you have to link that with what difference will this make, because it's what we sometimes call the so what question. So if you're able to do that synchronization, how does that change the world? And so okay. It's really a case of linking the critical data capture or data manipulation issue with how will this then make a big difference.
Great, thank you so much. I will continue the conversation with you off the line. Maybe we'll come back to you to invite you to our proposal team. Thank you so much, team.
Thanks.
Let me check if there are any questions from the audience. No question, Jimmy. Thank you so much. You take care.
Thank you very much.
We look forward to seeing you again. We actually miss you, Jimmy. Take care.
Thank you very much.
Thank
Take
you.
care,
Okay.
everyone.
Thank you. Thank you, my friend. Thank you.
Bye.
Bye.
Have opportunity other inconvenience. Thank you, Professor Anuba and Professor Lee. Next, we are honored to have Professor Yung Kwak give a presentation entitled Economics of Facility Standardization Case Study. Dr. Yung Kwak is a faculty member in the Department of Decision Science and Director of International Center for Project Management at the George Washington University School of Business in Washington, D.C. He also holds a visiting professor position at the Faculty of Economics and Business Administration at Ghent University in Belgium. Dr. Kwak is the editor-in-chief of the Journal of Management in Engineering, specially editor of the case study section for the Journal of Construction Engineering and Management. Let's welcome Professor Kwak, please.
Thank you. Should I start? All right, good. Right. Thank you. Thank you very much. Good morning, good afternoon, and good evening, everybody. I'm honored to present today in this very important conference. So today I will talk about the Construction Industry Institute's project that I just completed. So the final completion is by this December, which it took us 3.5 years. And we talk about economics of design standardization, particularly for the capital projects. So when I say capital project, is where the heavy investment type projects. So next slide. So other industries have successfully accomplished high levels of both standardization and modernization, and they have reaped those substantial benefits. The aerospace industry is one great example. The automotive industry is another example, as shown here. And then the shipbuilding or shipping industry is another one. So as for building design standardization, there are 3 questions that we might ask. First one is, has anyone bought a spec home in a master planned subdivision lately? Or been to any new fast food restaurant like McDonald's or like Target stores in those retail shops? Or how about a new apartment complex? You see that those are pretty much uniformly designed, so to speak. Meanwhile, the project costs in the oil and gas sector, and we call it a UMM sector, which is upstream, midstream, and mining sector, they continue to climb. Those costs continue to climb and has started to impact the economic viability of those capital projects. So while missing out on opportunities related to the standardization, particularly those design standardization, is acknowledged to be a problem in other sectors, this research, as I said before, was sponsored by the Construction Industry Institute's upstream, midstream, and mining sector, primarily the oil and gas sector. And the research was confined to that sector, but it also can be applied to other engineering and construction sector. However, as shown here, this issue has been a recurring theme in CII the last 25, 30 plus years, as it was discovered to have been mentioned as an unrealized opportunity by at least 6 prior research teams and their reports. For example, in the research team 245, they actually included a case study related to the benefits of standardization in low sulfur gasoline.
We don't see your PPT. You probably have to share the screen first. I'm sorry.
Oh my goodness. I thought that you would see the PPT.
Yeah, that's okay. I thought there's a technical problem, but you probably didn't press the button.
Everything, everything was set accordingly. Sorry, let me.
You don't have to feel sorry because we like to see you, but you know.
Yeah, I know, but you know, everything was set, and I was waiting in the waiting room for quite some time. So I want to make sure that share screen. I'm gonna share this screen. Do you see the PowerPoint slide? Oh, I turned it off actually. Let me see. 1 second. 1 second. Sorry about that. Do you see the one or one with the notes?
We can see the PowerPoint now. You probably have.
But is it with the notes or without the notes?
What do you mean notes? But I
mean, in the bottom, sometimes I scribbled some notes. So no notes, right?
What is the problem? Oh, yeah. We still see your notes. We still see your notes. So you have to
see my notes.
Yeah, we
so
see your
let
notes.
me then swap it.
How to? Oh yeah, that's fine now.
It's fine now. Okay. All right. So sorry about that. So I was around here, I think, right? Yeah. All right. So going back to that, going back to the CII project that I mentioned before, there are some previous research that is going on, and particularly in the low sulfur gasoline facilities, the benefits included savings of more than $55 million, or nearly 13% of total installed costs. And I like to point out that this research has verified the cost saving is only a part of the benefits of standardizing the facility design. The quick and more predictable project execution provides a significant portion of the value through the reuse of mature design. So while all sectors benefit and better understand and recognize its value, standardization is likely going to increase. The following is the definition of standardization. While all the words are important, let me emphasize some key points here. First is the consistency, which is critical, as that is the foundation of standardized design. Alignment is another one, which is a stakeholders is the key to preventing the unraveling of the whole program. And this starts with management buy-in. And then finally, optimization, which is the ultimate benefit. And as you will hear later, this applies to schedule as well as the cost. So the essential question for this particular research project was, how can higher levels of facility standardization be achieved in that UMM sector, the oil and gas sector, or the upstream, midstream, and mining sector? So in response to this essential questions, a pyramid of solution to increase standardization was developed, considering 3 management principles: the predictability, the agility, and the cost effectiveness. So the pyramid is comprised of 4 levels from bottom to top. First is the economics of standardization, and then the standardization decision-making model, and then what kind of critical success factors and enablers are out there, and also looking into the innovative technologies and approaches. I will focus on the three things: the economics of standardization, critical success factors, and innovative technologies and management approaches, and try to summarize this research. So first, let's talk about the case study. So what we have done is we collected data from 8 standardization programs, which had 45 projects in total to conduct this case study. Most programs had between 2 and 7 projects, and all of our projects came from those oil and gas companies and represented projects from various fields within the oil and gas sector, such as gas transmission, exploration, production, natural gas, compressors, stations, and others. So let's look at the cost savings. I'm going to give things up front. If you look at it, the total installed cost, which includes the operation and maintenance costs, and the customized project is 100% line, given that baseline, compared to the customized projects by looking at the savings by functions. Overall, all the functions saved in cost. Compared to a customized project, the program saved the most cost in engineering and procurement, which almost is 50%. Overall, we saw greater than 10% of total installed cost savings. If you consider the dollar range to complement the percent data, 35% savings equates to $1 to $5 million. So to give you an idea, one of our case programs saved more than $22.5 million in engineering when compared to applying the conventional approach from 7 standardized projects. This program saved $34 million in total. So that's a huge amount of cost saving right there. Let's look at the schedule savings as well. So program saved schedule is again in engineering, procurement, and operation and management, which is about 65%. And then the fabrication, construction, and commissioning and startup save 5% to 10%. Overall, the program also had savings to all the functions in schedule. Depending on the size of the projects in your program plan, the repeat schedule savings can be very significant and help project teams meet stakeholders' schedule expectation to capture the market value. So to give you an idea, one of our case programs saved 19 months in engineering when compared to applying the conventional approach from 3 standardized projects. This is 100% line with a conventional customized project. So program 1 through 8 shows a constant trend of decreased engineering costs as the number of units or projects increases. Program 1 initial project went from 100% to less than 60%. Program 8 didn't require engineering redesign, and this is quite awesome if you think about it. The traditional program spends 100% every time for custom projects. Here you can see, you can check the percent duration spent trend by the number of units on engineering by different programs. Again, the 100% line is the conventional customized project. We can also find a constant trend of schedule decrease as the number of unit increases. So then what was the actual life cycle cost and schedule savings compared to the conventional methods for their standardized project? Overall, 8 standardization programs save of 25% life cycle cost and 15% schedule in average. This provides market value for both total installed costs of a project and time to the market, which is having a better schedule predictability. So imagine being able to provide a company and stakeholders a predictable and repeatable cost and schedule savings from your standardization efforts. Through our case studies, again, cost effectiveness, agility, and predictability objectives are met and often exceeded its expectations, but also safety, quality, and schedule performance met or exceeded those expectations. So now I'm going to briefly look at some of the specific case programs in more detail. The first case program we'd like to introduce is a unconventional well paths with project level standardization. The standardization program initiated back in 2012 and it still continues today. And there are 3 generations of standardized projects. The design team, what they done is that they created 7 standard components for the well paths as represented in those Lego pieces. So think of it as a Lego pieces. Those are all sort of a pre-existing engineering design. And this is an example of a single well site design which use only 5 of the 7 components. So the drawing package would include the standard drawing packages for the 5 components used and would not include the coupler or the flare drawings. Those are pretty simple to do it. But this is an example of a 12 well site configuration utilizing all 7 components. Each generation of program resulted in a savings in total installed costs upward of 57%. The second case program is a gas transmission project with a project level standardization. This program has had 4 sub-programs with different generation of design, which includes 16 gas transition projects in total. When it was focused on engineering, drafting, data sheet and requisitions, procurement, and project management and administration, 50% work hours savings were gained, which led to 50% of cost savings. So this is an ongoing program. So the information about the actual construction is not available, but you can see a tremendous saving of the cost itself. Let's look at case number 3. This program relates to standardization of facilities in the upstream oil and gas sector. And it was an effort to progressively mature the standardization of a satellite, which is one of those facilities, the testing facilities. Various standardized components were utilized in a standardized comprehensive system design. And the team kept asking the question, how many times are we going to build the same thing without standardizing it and then realizing those benefits? As for the economics of standardization for the entire upstream capital program, for the engineering, through a 20% reduction in engineering cost, 2% reduction in total installed cost was realized. In terms of material and labor, 7% improvement in total installed cost for material and labor was realized. And the findings and development, overall findings and development costs saw a 5% improvement in the associated projects. This program is a natural gas compressor station projects in system level standardization. The program initiated in 2014, and so far they have executed 7 standardized projects. The savings may not be immediate. Also, as shown, there may not have been substantial savings in cost. However, there was an improvement to the predictability of the schedule, at least when the oil and gas sector was hot, and the most important factor was not the cost to build a facility, but to be first in the market to start pumping the gas. And when you have a better predictable schedule, that was a worthwhile thing to do. Now let's briefly look at the obstacles of design standardization. We have investigated the reasons for not realizing the full standardization potential from the case programs here. But still, there are a lot of challenges, particularly in the oil and gas or UMM sector. And these are some examples: the leadership, project manager, project team, scope design, supplier, implementation in a different region, different operational and maintenance team, and others. So now let's look at when to consider and how to achieve higher level of facility standardization. So there are 2 levels of assessment in this particular model, and they align with the project phases. So when you're in the FEL 0 or FEL 1, the conceptual phase of a project, you will want to do the level 1 assessment. And level 1 looks at high levels and the key issues. A strong score in level 1 indicates that your project or the suite of projects might be great for standardization. At that point, save the assessment and then continue to advance your project with the standardization. Then come back in the FEL 2 and 3, and in that second level of assessment, level 2 takes a more detailed look at the benefits, drivers, risk, and other impediments of design standardization. Now, let's briefly talk about the critical success factors of standardization. So we started with 92 factors and condensed and reduce it to 15 critical success factors. Again, I'm not going to read all of the 15, but I'm going to boil it down to 4 heavy hitters. So there are 4 critical success factors that have a high impact on the success of standardization, but currently have a low implementation rate. So you want to hit the one that is low, but has a great potential. These are the heavy hitters we want to bring to your attention. And this is where the industry can advance, and we can do it right now. First one is alignment and approval of being conscious. Second is discipline to maintain standardization, which is having a commitment. Third is design, having a design standardization approach, which is having a defined plan. And the fourth is having a constructability of standardization. And going further, what parts of construction can be standardized, subcontracts, or test packages. Then we look at these critical success factors and look at 2 things. Who is responsible for them, and when do they need to be implemented? Now let's look at the technologies and management approaches or management principles for standardization. First, here are the top 6 so-called upcoming innovative technologies. Modularization, the standardized piece and part and mobile device should be more familiar to us, but things like construction simulation technologies, intelligent automated data collection, and LiDAR, they are definitely forthcoming, and I've seen in the keynotes and the paper that many authors are actually presenting related to those technology applicant projects. So here are the top 5 management approaches, which is the management principles that have both high impact and high likelihood. You will notice that these themes are also in those critical success factors, which is alignment and commitment. But also having a formal lessons learned program where for example, if you are building 5 plants in succession, you can take the lessons learned from the first project and apply those to subsequent projects. Finally, please take a look at the standardization benefits and trade-offs scale. As you can see here, benefits, it's weighed a little more heavier. So with the median 25% life cycle cost savings and 15% schedule savings, the case project actually confirmed that the standardization benefits outweigh the trade-offs. So do you think that this engineering construction industry, specifically the UMM sector, is missing out on those opportunities for standardization? So I'm going to stop here. And I would like to thank and recognize all the research team members who participated in this research. There are more materials. If you have any questions or papers, I can forward them, but I'm going to stop here and entertain any questions. Thank you.
Thank you, Professor Park, for your nice presentation. Now, may I also invite our moderator, Professor Heng Li, for holding the Q&A session for us. Professor Li and Professor Park, please.
Professor Park, thank you so much for your very comprehensive presentation. You actually gave a very good presentation on, how design standardization can bring time and cost savings. But as a technology advocate myself, I have actually a question and also a doubt. Do you think, are there any clear evidence that the adoption of this advanced technology such as BIM, virtual reality, Internet of Things, AI, can really bring real time and cost benefit to the industry? Are there any evidence?
So we have to look at, that's a great question. We have to look at the past. In the past 20, 30, 40 years ago, when the whole information technology area started to emerge, and when there are a lot of companies trying to automate their business process, they had the same question, whether they have those upcoming technologies, upcoming IT applications, are they really helping or the overall effectiveness of the management of the companies? And there are tremendous amount of studies, and the answer is yes. And so I believe those technologies, so we have to think both technologies and management together. We cannot think separately, because if you think in one way and just focus on technology, then it's not going to work well. Or if you just focus on management, it's not going to work well. But obviously, all those upcoming technology is definitely help, and it's going to help the project perform better.
Yeah, thank you so much for your answer. I think that is very helpful, because I noticed in both academia and industry that the people seem to forget that time and the cost are ultimate objectives that we want to achieve in our industry. Because, for example, in the industry, in Hong Kong in particular, the government is advocating the use of this technology as a mandate in many of the projects. They actually say this for the sake of just promoting the technology without any real evidence that this technology will bring any benefit. And also in the research domain, I noticed that if you don't, study or publish in technology, and your papers often will rejected by some of these mainstream journals. I think we should refocus ourselves on what are the essence of the work we are doing. What is the the real purpose of our work? So for that reason, I think that you have brought the fantasy to reality in that sense. So I really like your presentation. Thank you so much. And,
Thank you. I just want to pitch for one minute. So
yeah.
I know there are a lot of excellent technology-related journals that scholars want to publish. But as you just mentioned, that whole management side, the economics of technology, those are equally important because those are always a question that the executive or senior managers ask because it's not cheap. If it's very cheap, then they would not care. But oftentimes, adopting those technologies are very, very expensive. So there are a lot of studies that are needed. And for example, Journal of Management Engineering, which I'm serving as editor-in-chief, we will be happy to review those papers. Thank you.
I can't agree more with you. Thank you so much. And I like the journal you are editing. I think the journal is doing extremely well. And my colleagues, Dr. Sil and I often think that we would like to work with you to, to do a special issue on specifically on the theme of how digital technology will impact upon the project time and cost performances. So maybe I need.
That's an excellent special issue topic. And once you have a draft, send it to me. Then the editor board will review it and then approve it, and we go from there.
Thank you so much for your support. Great to see you. Thank you. You take care. Thank you.
Thank you. Bye-bye.
Bye-bye.
And Professor Lee, for your discussion. Due to the overrun issue, we would like to skip the break session. So sorry for that. Now we will proceed to the next session of today's conference. I'm Wei Chen from Hong Kong UST. It's my honor to be your MC today. In the next session, all the speakers will have 20 minutes presentation and follow with the Q&A session. For audience, please feel free to raise your question using the Q&A function. Let's welcome Professor Sang-Yu Lee. He will be presenting on the topic of the anthropocentric construction management. Professor Lee is a professor and is John Tishman Faculty Scholarship at the University of Michigan and leads the Dynamic Project Management Lab. He received both his master and PhD degree from MIT, and he was chair of ASC Construction Research Council, chair of ASC Visualization Information Modeling and Simulation Committee, and the boards of governor at ASC Construction Institution, among others. He has 5 editorships in leading journals like the ASC Journal of Construction Engineering and Management, and he also received the numerous awards. Okay, let's welcome Professor Lee, please.
Okay, hi everyone. Let me first make sure, let me share the screen. Okay, first of all, thanks so much for inviting me for this exciting joint conference. It is finally happening, so I would like to appreciate the committee's effort to make this happen. Today, I'm going to talk about the anthropocentric, human-centric construction management. In the construction industry, the construction worker is one of the most important resources and asset in our industry. So these construction workers are dealing with a lot of different construction dynamics, meaning that things are changing over time. For example, evolving site conditions. And also they have to meet the required performances like productivity, safety, and quality issues. And one of the current issues at the many countries are experiencing is aging and lack of skilled laborers. At the same time, nowadays, they are asked to work with the new emerging technologies. And robots are coming in the site. And they are also asked to use the AR and VR devices. And drones are flying over the site, and ground robots are in the ground in the construction site. So the construction workers are getting a lot of pressure to deal with all the different things. So they are the ones who built and maintain our infrastructure, where we maintain our daily lives. But so what we are trying to do is taking anthropocentric approach, basically human-centric approach, to best serve them for their value, inclusion, and experience in their careers. So today, particularly, I'm going to talk about the anthropocentric approach for safety issues. Safety is very important in the construction, and in the many different countries, we suffer a lot of the different accidents in the construction. And in case of the United States, the construction has the highest number of fatalities among all other industries in the United States. So what we are trying to do is using the minimally invasive means like new technologies, computer vision-based mobile devices, and wearable biosensors to make sure to support them to be preventive about the construction accident. So I'm going to talk about the two use of the two different technologies, computer vision and wearable biosensors. And let me start with the computer vision-based application. So first example that I'm going to talk about the proximity prediction. If we look at the statistics, contact-driven fatalities is 41% of the total fatalities in construction in case of United States. So contact-driven accidents means they struck by and caught in between. So one of the fundamental requirements to avoid these contact-driven fatalities is to understand the proximity between worker and the object, for example, the heavy machinery. Beyond that, what we really actually need is predicting the proximity, because identifying workers' proximity with heavy machinery may not enough to avoid these contact-driven fatalities because it may be too late. So what we are trying to do, work on, is to predict future proximity based on the computer vision. So the example that I'm going to show is using the drone and camera-mounted drone. So the first step we tried is the tracking and the object over time. So nowadays, a deep learning-based object detection and tracking has been widely used. So we track the object in a real-time basis. And then we try to measure the distance between the moving object, but the camera is mounted on the drone. The view angle from the camera in the drone has to be rectified onto the ground level to measure the distance between the moving object. So we applied coordinate rectification, and then we predict each object trajectory for next 5.28 seconds. So because we are predicting their trajectories about 5 seconds earlier, so that it can give a room for workers or equipment operators to react to the potential proximity. So particularly, we use the conditional generative adversarial network, conditional GAN, for trajectory prediction. And GAN has been widely used, and particularly we apply the conditional GAN, which use prior information rather than noises. So it is capable of generating a future trajectory more conform to the past history. So this is the demo video. Hopefully the resolution can be stayed throughout this bandwidth. So basically you can see that we are tracking the object and then we predict their future trajectory for the next 5 seconds. And then you can see that different colored lines are there. That is future trajectory. So every 5.28 seconds, we are projecting their trajectory, and you can see that they are following very well to our predicted trajectory. So the current accuracy that we have is average proximity prediction error is 0.95 meters for 5.28 seconds prediction. So this is to make sure to implement predictive safety using the computer vision. Another example with the computer vision that I'm going to introduce is for the ergonomic injuries and risk. So in case of non-fatal injuries in construction, the highest proportion of non-fatal injuries in construction is overexertion and bodily reaction. Basically, we are talking about ergonomic injuries. And these ergonomic injuries coming from the ergonomic risk factors, which is awkward posture and repetition and the excessive forces. So what we have been doing is, again, we are talking about minimally invasive means. So we use the mobile camera, like a smartphone. And using the smartphone, using the computer vision, we are going to capture the motions. basically postures and repetition. And then we are going to estimate forces without attaching any sensors to workers' human body. Just using computer vision based, we are going to estimate the force. So the way we do is first is a 3D pose estimation, 3D pose estimation, deep learning based 3D pose estimation, and then go through kinematic modeling, force reconstruction, and force optimization. Then we are finally estimate hand and foot process. Specifically, for in this case, kinematic modeling is to understand physical constraint of all the body part of the human. And then we reconstruct force based on the physics. So basically, once we identify physical constraint of each body part, we can identify potential range of the forces based on the physics-based equations. So we reconstruct the forces, and then using the recurrent neural network, we optimize the forces so that we are able to estimate hand and foot forces. So here, the left side, you can see the subject is wearing all the force sensors. That is for the measure the ground truth force data. And then using the smartphone, basically mobile camera, we create a 3D pose. And then you can see that we predict push force of the right hand only with a smartphone. So the orange lines are showing the predicted forces, and the white lines are basically measured from the ground truth force sensors. And you can see that where peak force are happening, and also the magnitude of this peak force has been pretty much accurately predicted by computer vision approach. So what this means is that basically only with a smartphone, not interfering with the worker's ongoing one, we are able to on-site biomechanical analysis, which means that how much stress has been exerted on each body part over time without attaching any sensors to the workers. So those are basically two examples of the using computer vision to assist the worker safety and health. Now, let me talk about the use of the wearable biosensors. So particularly the wearable biosensor that I'm talking about today is EEG, which measures brain waves, and the wristband, which measures electrodermal activity and the heart rate. It could be different form factor, like nowadays we can also see the ring tie, which can also measure EDA and the heart rate. So what we are trying to do is, if we look at the construction accident, and many of the accidents are associated with unsafe behavior. And these unsafe behaviors, what we are trying is to understand the worker's physiological response, which is a precursor of this unsafe behavior. So what do I mean by the physiological response? For example, stress, and how also the fatigue, or even their emotions. So for example, if workers get stressed, they do make a mistake or they do awkward things. Also, if workers get fatigued, they are making mistakes. So we are trying to understand workers' physiological response as a precursor of the unsafe behavior. So one specific example that I'm going to talk about is a stress in construction. So basically the mechanism of the stress is, if we have excessive stress, it increases the cortisol hormone, and then our attention is going to be selective. We are losing ability to see things comprehensively, which is causing near misses and accident. Another thing is that the stress is causing is a decrease in dopamine, which is also causing depression and discharge, which is again causing the mental health issues. So mental health issues in construction has been a little bit underestimated, but now under this pandemic, people are really talking about now mental health issues in the construction workers. And you can see that a lot of people are talking about the mental health issues under this pandemic. So understanding this stress becomes even more important in nowadays construction. So we use the EEG, which measures brain waves, and to understand workers' stress level. I'm not going to get into about the EEG based, but the EEG, the benefit of using EEG to monitor the stress is it provides very rich information about the stress. However, it's a downside at this time is because of the limitation of the hardware, it is a little bit hard to use this wearable EEG on the hardware for a long time. Of course, it can be used for a certain amount of time, but apparently it is not practical enough to be used for continuous monitoring of stress in the construction site. So another thing that we have done is using basically wristband, using the EDA, electrodermal activity, which measures the electric property of the skin, and PPG, which basically measures heart rate. So that using the wristband, we are going to identify workers' stress minimally, invasively. And also at the same time, this wristband becomes very affordable nowadays. So it could be very widely deployed to the construction workers without investing a lot of money. Also, if you think about the ecosystem of the construction industry, it is definitely help to prevent any health and safety issues in construction. So there are several insurance companies are willing to pay or decrease their insurance premium as a way to promote these wearable biosensors. When we apply the wristband type and to the wide deployment, one of the most important issue is the contextual and individual difference in learning our machine learning model to identify the stress. What I mean by that is there are so many diverse stressful situations in construction. So even though we train the model with mimicking a certain stressful situation in the lab or in the real world, it may not guarantee that we are going to observe all the stresses in the field from our training data. So there are unforeseen, the unseen data can be possibly available, which degrade performance of the stress identification. Same to the subject. We can train our model with a handful of the subject, or even we can increase the number of subjects, but all the people react stress in a different way, so their physiological response can be slightly different. So even though we increase the number of population for our training data set, there is still a chance that our performance is not going to be what is supposed to be. So what we are trying to do is we need to address the need for context and subject independency. So what we have been doing, the stress detection method, we use the deep learning based convolutional neural network and LSTM feature extractor, as well as domain adaptation. So domain adaptation is a technique to generate a domain independent feature map, minimizing data distribution discrepancy between different domains. So here different domain means the subject and context that I just talked about. Then we try to validate, particularly for context and subject independency. So what we did is we have 10 subjects, and each subject will go through a different stressful context. For example, stress, solving the math, or unpleasant movie, or physical exercise test. Then we proposing leave one context and subject out cross validation. So what this means is when we test this wearable-based the algorithms to detect the stress, so our test of target is, let's say, subject number 3, stress from mess. Then we train model with the other 9 subjects, the other stressors like a movie and exercise. So excluding subject number 3's stress coming from the mess. Then we repeated these trials 30 times, which is going to be a cross-validation. So we propose this leave one context and subject out cross-validation. And one of the most widely machine learning technique to detect stress in the literature is a Gaussian SVM. So their typical accuracy when they applied K-fold cross-validation is going to be 80%. That's a state of art. But when they apply, then be applied with leave one context subject out cross-validation, basically they can be context and subject independency, their performance is dropped like almost 60%. And even though we can apply the deep learning, K-fold validation, they have achieving higher accuracy, like 80%, but still, when we apply this leave one context and subject out validation, their accuracy is slightly over 60%. So then when we applied our method, which used the domain adaptation, we can still achieve 8.5%, which means that regardless of the unseen context, and unseen, untrained subject, we are still be able to identify a stress. This can be helpful for wide adoption of these wearable biosensors to detect the stress. So what we have been working on now is the keynote speakers like Buchu and Shimei also talked about the digital twin. So digital twin, I believe that the other also keynote speaker will talk about a lot about the digital twin. So particularly in my research lab, we are trying to create the anthropocentric digital twin. So based on the beam and the computer vision and the IoT sensors, but also at the same time, we are trying to integrate the individualized physiological status data so that when and what kind of the job is causing, for example, a stress, fatigue, and which time of day they get stressed or fatigued or bad emotions. So we can see that individually address their concern to best serve them for their performances. Now, let me briefly talk about this wearable-based approach for the other application, particularly in this case, infrastructure management. So the specific topic that I'm going to talk about is application to seniors' stress in the use of the built environment. So we are experiencing the growing population of seniors in the most countries right now. So it is expected that 20% of all the population will be basically seniors within several years. So seniors experience impaired capability. It could be physical and cognitive capability. And if those capabilities are less than environmental stressors, then they will experience the stresses. So what this means is that if they experience the stress from their built environment, so what is causing is a mobility limitation. So limiting mobility is extremely important issue, particularly for seniors, because all the seniors basically would like to live independently. But if mobility is limited, there is no way that we can achieve the independence. So what we are trying to do is that mobility is very important for seniors, the independent living, then how we understand senior stress in the use of the built environment using a wearable biosensor approach. So we use the same wearable wristband, we use the same stress detection method, and then we can identify the stress level from the seniors. However, one important issue in this case is even though we see the stress from the seniors while they are using their built environment, we don't know the stress is coming from that spot of the built environment. Because when a senior work around use their built environment, let's say they got stress from the certain spot. Yes, of course, it can be from that spot of the built environment, but of course, maybe it can come from some other stressors. For example, maybe a dog is barking at him or her, or he or she gets stressed because of his personal life. So the approach that we are taking is called collective sensing approach. To make a long story short, so for example, let's say 7 out of 10 senior persons get stressed when they work around that particular spot of the built environment. Then it would be safe to say that their stress is very much related with that spot of the built environment. So that is the way that we detect the stress hotspots. So we work with the East Clock Tower Senior Apartment. It's a senior residence. And we recruited 30 senior subjects, and they wear the wristband, and they also carry the GPS for 6 weeks, 2 weeks for each season for their daily life. And we applied our stress detection method to identify and collective sensing approach to identify their stress locations while they are maintaining their daily lives. So this is the detected stress hotspots around their residence. You can clearly see that there is some environmental stresses coming from built environment. For example, vertical gap, side slope, wide joint, and vertical displacements all are identified as a stress from their built environment. One interesting finding is that These parking areas are also identified as stressors for the seniors. So we had a follow-up survey and interview to identify why these are stressful for them. And what they are saying is that this parking lot, also cars are passing by in this parking lot. So it looks very normal to us, but the seniors park the car and getting to the mall or destination requires to deal with all the pass-by cars, which is very stressful. So what this means is that when we design and when we maintain our built environment, if we look at the eye of our normal population, these are not stressful at all. These are very normal, but it could be very different story to the seniors. So the way that we apply wearable-based sensing approach can be actually be very useful to identify such a stress hotspot in a very continuous way and also non-invasively. So I think this can give us a great lesson for our future development of the smart infrastructure and smart city. And now we are all talking about smart infrastructure and smart city. And one ingredient that should be in the smart infrastructure and city should be inclusion. So we have to include the disabled person and the senior persons to maintain their independent living through this built environment. So I think this approach can be very useful to achieve that objective. So let me conclude. So basically, I'm taking anthropocentric approach for construction workers. Particularly, I have been using minimally invasive means like computer vision and the wearables. The idea is to best serve human workers for value inclusion and their experience. So I would like to finish my presentation with my acknowledging my current student and also my funding sponsors. I'll be happy to answer any question that you have.
Thank you perfectly for your nice presentation. You provided us with more ideas and new concepts. Thanks. Now, may I also invite our moderator, Dr. Jin Ho So, organizing committee chair of our conference, for holding the Q&A session for us. Dr. So and Professor Lee, please.
Okay, thank you, Professor Lee. Thank you for your interesting presentation. And I'm very happy to see you online here.
Very nice to meet you, Juno. It has been a long time.
Yeah. Okay. While we are waiting for the audience questions, so let me ask one quick question for you. Okay, my first question is, okay, I strongly believe that the use of the computer vision technology and the wearable sensing technologies could open the door for more proactive construction work monitoring, especially to reduce some safety and health issues. And also, it can be, of course, it can be applicable to the built environment to monitor the elderly people as well. But also, probably you may know that I'm also working with the local contractor in Hong Kong to apply these technologies. But many contractors are very interested in using these technologies. But when I talked with the individual workers, I feel actually they may be reluctant to use these technologies because they could feel they are being monitored. So could you briefly share some experience resolving these kind of issues in the United States when you apply this technology in practice?
Thank you, Professor. This is actually a great question. I think one of the most important questions in these research areas. So when we work on this research, we actually work with more than 100 construction union workers to see their acceptance level for this, for example, wearable biosensor technology. And our finding, working with more than 120 construction workers, is that they are not interested in using this technology for productivity monitoring, but somehow it is going to help for their safety and health, not involving with management. They really would like to try this technology as long as it is very helpful. So I think that's why I briefly talked about the insurance company. I don't think we really need to bring the contractors and subcontractors directly to this kind of technology because it's so affordable now. I think the insurance company is willing to pay. So I think if you look at the ecosystem of construction industry, the insurance company make a big law, not necessarily involving the contractors and subcontractors. Also, at the same time, different generation have a different idea of use of this technology. So when we actually studied that, the older generation would like to see the usefulness of this technology, but the younger generation are more interested in my coworkers are using that. They see the value of this technology already because they have been using it, right? So I think my answer would be we need to look at the whole ecosystem of construction industry, not necessarily involving the contractors and subcontractors. And the second, we need to look at the different generations, and we can create the different strategies for them to work. That is my answer for you.
Okay, thank you. That totally makes sense. Okay, thank you for your answer. And I got one question from the audience. Let me read it for you. Okay, what do you think about considering other factors to predict the stress of the construction workers, such as the construction site situation? I think it is possible to estimate the cause of the stress if the conditions of the construction site factors are applied as in the case of the elderly residents.
Right, I think this is very interesting question. I have a vision to identify using this technology, what is causing that particular stress. But with the current technology and current advancement, we are not there yet. Of course, I would like to go there. But I think the more the practical application would be what type of stress that we are getting, rather than what are the stresses. Because eventually what you want to do is manage stresses. Then the wearable biosensor, particularly the reason that I like this approach is to measure people's responses. So different stressors are giving to different responses. So that once we identify different responses, basically we would like to intervene to different responses of workers. That is our objective. So I think my answer would be yes, we would like to identify different stressors, but realistically, our approach should be what is the different stress reactions that we are having so that we can manage them.
Okay, thank you for your clear answer. I strongly believe that it would be enough to answer this question. Okay, for the sake of time, I think that I need to finish your presentation now. And thank you for your presentation. I hope to see you in person soon.
Yeah, I will hope to see you soon. Thank you so much for listening. Bye.
Thank you so much for Professor Lee and Dr. So. Now, may I invite Professor Carl Haas to give the presentation on the topic of construction and deconstruction, moving the built environment towards a circular economy. Professor Haas is the chair of Department of Civil and Environmental Engineering, and he is a university research chair at the University of Waterloo, Canada. He serves on a number of doctoral bodies and on professional committees for organizations such as ASCE, ASERC, IAARC. Professor Hart received a lot of awards such as the CSCE Walter Shanley Award for his outstanding contribution to the development and practice of construction engineering in Canada. Let's welcome Professor Hart, please.
Hello, and guess I'm waiting for an invitation. Is that correct, or do I share my screen now?
Yeah, Professor House, you can share your screen.
Okay, thank you. Okay, I got that now. Thank you. There, we'll try that. Share. And okay, so good tomorrow morning, everybody. I hope I can interest you this morning in some research around construction and deconstruction and the role they'll play in moving the built environment toward a circular economy. So my name is Carl Haas, and I guess you just had an introduction. I'm a professor in civil engineering at the University of Waterloo. What I'll present today is the result of collaboration amongst my colleagues and research funding partners and students, and I'll focus on a few of those students whose research is in some way related to the theme of transition to a circular economy. So what motivates us to work toward a circular economy in the built environment? One of the most obvious or biggest motivators to us is waste. There's hundreds of millions of tons of construction and demolition waste produced in the US every year, including Canada. And around 40% of this waste is reused, recycled, or sent to waste to energy facilities, which is good, but it means that about 60% of the waste is being dumped directly into landfills, and much of the recycling ends up there as well. So we're depleting the world's biological and abiotic resources in a way that's not sustainable. Adopting circular economy principles would help us reduce this waste. According to the World Economic Forum, the people who produce the Davos conference every year in Switzerland, adopting a circular economy principles could significantly enhance global construction industry productivity, saving at least $100 billion a year. So this finding is one of the reasons why the Construction Industry Institute at the University of Texas launched a research team recently on circular economy opportunities in construction. We started with a global scan of circular economy commercial initiatives. And one of the key findings from this preliminary scan so far is that there is a lot happening already. Okay, so what I will talk about this morning is some of the research we're doing in construction and deconstruction and how that helps move us towards a circular economy in the built environment. First, I'll share Mohammed Mahdi Sharif's research in dimensional fabrication control. So this research is driven by the observation that, at least in the industrial infrastructure prefabrication sector, we still make things that don't fit and that cost and that results in tens of billions of dollars in waste and rework per year. And the stuff doesn't fit because the measurement and comparison tools that we're using are old and they don't work very well. So our research objectives over the last 10 years have been to make better measurement and comparison tools that can be used by the craft workers. They're simple enough that they can be used by craft workers on the workface. They can be used remotely and they can facilitate better collaboration. We do this mostly by developing algorithms that help it make it easier to compare a 3D design with scans of parts of the design being built. We also make use of the cloud to support collaboration. And this research has progressed from early theoretical work with lab scale assemblies to years of research and deployment in real fabrication facilities. We're agnostic about how we scan what we're fabricating, as long as we can get a point cloud of it and its surroundings. Clearly, the accuracy of the scanner drives what we can do in terms of the fineness or the roughness of the errors that can be detected and measured. In the simplest rendering, you can see that we typically compare a point cloud version of the design with a point cloud scan of what is being fabricated. And the best way to make this easy for a craft worker would be to automatically find the object in a point cloud, but doing that in less than a couple of seconds is hard still. So we use some human-machine interaction. We think that's okay as long as it only requires approximate indications and simple input. So once the as-built scan is overlaid on the model, the worker knows if the assembly has any geometric defects and can visualize them. And of course, this can be done in augmented reality as well, but ergonomics and precision and form factor in a working environment is critical. So we have to think about that as well. In later versions, ends of the assembly can be locked and deviation measurements can be made. And this general approach can be used for many types of assemblies. And of course, there's a lot of excellent research being published on advances in related areas by other researchers. And this just is a general idea of what sort of things can be done and checked. And this area of research is can be easily Googled. There's some publications around it. The research also has led to commercialization into highly scalable cloud-based software as a service solutions. One example is shown here. And I think it's an example of the trend we're observing in construction towards digitalization, digital twins, vertical integration, and prefabrication. And a related trend is a second wave of construction, more robotics, more centered on human robotic integrated systems. And that's what we'll take a look at next. I'd like to share some of the human robotic systems research being led by our senior doctoral student, Mr. Ryu. And this involves a lot of analysis using motion suits and 3ds, SPP, and other software to work out joint loads. So far, this project using these sorts of tools focuses on 4 main topics, which are advanced ergonomics assessment, workplace design, fatigue detection, and automated training tools. And the studies actually have been quite extensive in terms of collecting empirical data. We've built over 60 walls with 60 different craft workers at different levels of craft development, or sorry, apprenticeship development. And one of the things that we validated in these studies is a jerk can be used as a metric of physical, as a direct metric of physical fatigue. And you may remember from undergrad days, a jerk is a different differential of acceleration. So there's good empirical evidence that this is a direct way to measure fatigue, and it's published in that attached article. We also study the impact of self-leveling pallets as maybe one of the simplest forms of human robotic systems. What it does is it maintains a constant pick height for the craft worker. And by maintaining that constant pick height, it reduces the lumbar compression forces by up to 40%. And it also improved productivity by over 10%. So it's just sort of a general area of research, but the people who we work with would like to look also at fully automated systems and exoskeletons. So this and virtual reality training systems. So this work is ongoing, and it's published as well. So I'd like to return to the theme of the presentation and touch on some examples of our current research that's more related to deconstruction. Yongwei Zhao is a senior doctoral student working on problem of optimized packing of irregular 3D objects. And my son pointed out the other day, because we were making Christmas cookies by putting our presses into a flat roll of dough, that this problem has existed forever. And I know many of you know that the two-dimensional problem has existed forever, and it's been very well studied. But why do we care about optimized packing of irregular 3D objects? And it turns out there's lots of reasons for that. There's a lot of nuclear power plant decommissioning, and how effectively we pack broken and cut waste pieces will save hundreds of millions of dollars per power plant, but it's also applicable in 3D printing, shipping, and adaptive reuse. So far, we've explored 3 general approaches to the irregular 3D object packing optimization problem. So one, we tried a packing algorithm based on geometry constraints using scanned point cloud data and meshes. and did some studies. This was using our own sort of physics engine that we developed. But then we also tried using meta-heuristics, including genetic algorithms and simulated annealing. And we used off-the-shelf stuff like Rhino, Kangaroo physics engine, and an evolutionary solver that I forget the name of, sorry. And we used this to conduct a whole bunch of experiments to see what would work best. But we also thought it would be interesting to see if you scanned objects and you imported them into a virtual reality environment, could humans with a scoring system come up with really good plans, and would that work better for multi-objective optimization? And so this is done in the, this is a very crude early example of what we're doing in the Unity gaming platform. Another area of our research related to deconstruction in the circular economy is product recovery management for improving the net environmental impacts of reuse, renovation, refurbishment, and adaptation projects. And Ben Sanchez, who's now a professor at Monterrey Tech in Mexico, drove most of this research. Ben developed methods to compare construction cost and life cycle impact of new build and adaptive reuse solutions to capital project goals. And just looking at this substructure and superstructure, he, in one case study, he found, and it was pretty typical, that adaptive reuse was a cheaper solution for this part. But for categories of work such as exterior cladding, it doesn't actually reduce construction cost. What we did find was that it almost always resulted in substantial environmental impact savings. So adaptive reuse over new construction. So then we got curious to see how alternative deconstruction methods and adaptive reuse projects would impact final life cycle impact and deconstruction cost. And it was also interesting to see if deconstruction could be automated, deconstruction planning could be automated and optimized using selective disassembly planning. So the question is, where would this level of planning make sense? Understanding the BIM level of development required in the site conditions assessments. And we think that for highly repetitive building subsystems, it will be useful. So just to explain in a tiny bit more detail, there will be options for each connection. We assume there are, that discretized, we would say perfect disassembly, destructive disassembly, selective demolition. And each of these options will have different costs and life cycle impacts associated with them. And typically there's a trade-off between deconstruction method cost and life cycle impact. So we looked at how all of the possible disassembly sequencing options could be automatically generated from a semantically rich BIM model, or BIM, I should say. And then we could find the proto-optimal frontier of disassembly sequence solutions that would provide a trade-off function between cost and environmental impact for a particular building system or subsystem. And that's what you're seeing on that graph on the right. So in the next research example, we eventually arrived at a very similar trade-off function for a related adaptation and renovation design problem. This research is led by Shada Shahi, who's another one of our senior doctoral students, but also several industry research partners and collaborators were involved, and this was just really one part of her research. It's driven by the idea, by the problem in Canada, at least, in a lot of Northern Hemisphere, that adaptation of dated residential towers is an urgent issue due to the aging of the housing infrastructure and the growing demand for affordable housing and the poor energy performance of these buildings. However, as in most design problems, an extremely large number of solutions are possible, and exploring them finding a solution is costly. So computational design methodologies have the potential for facilitating optimized design strategies driven by improved energy performance and reduced life cycle carbon emissions. Also, modular construction can increase efficiencies in the design and implementation of building adaptation projects, and it can minimize construction waste. So in a functional demonstration of this computational design framework, a fixed set of extension options are considered. And an extremely large number of adaptation scenarios that conform to a set of design constraints are evaluated based on multiple conflicting objectives. But I see that we're running a bit tight on time, so I'm going to skip over the framework. It's a bit dense, and just talk about how it works. So on the left, you see the rules for modular additions. It's a demonstration of the stage 1 of the framework, where an existing building is analyzed and the dimensions, extension location, and patterns are identified. The paneling and assemblies for the module options are determined, and the extension possibilities for each of the units are set based on unit layouts and logical possible extensions. So on the right, in stage 2 of the framework, you see 2 of the generated design options using the computational algorithm. And what you see are some of the energy and daylighting analysis results that were done for each of the design combinations. So 600 design permutations were generated. I think it took 2 weeks of constant computing. And even then, these really just present a set of alternatives that we could refine further. So what we did was structural complexity, which is the horizontal axis, is used as a proxy for construction cost. And then you see there's a clear trade-off with potential life cycle cost in terms of the number of modules, daylighting, energy use, and embodied energy. And this is this Pareto optimal boundary or trade-off curve that I was alluding to when I was talking about Ben's research. So these are some of the design options generated, and the Pareto optimal options in the previous example are represented in the top right, and the secondary options are in the bottom right. So the results of the study demonstrate the practicality of using computational design methodologies for the integration of modular construction in the adaptation of concrete residential towers. In sort of simpler and related research, Chris Rausch has worked with another set of our partners to develop smaller scale engineering solutions to similar problems. While much of Chris's work in geometric optimization has been in tolerance management, this is an interesting and related extension, I think. So coming full circle to the theme of this presentation, one of the solutions often proposed for a circular economy in the built environment is designed for adaptable configuration. So that uses can change over time as necessary. And examples of options available with this modular system are multi-story residential units and single unit or single resident extensions to existing housing in order to achieve urban infill. So this was in Kitchener, the city I live in. But also such buildings could easily operate as modules and materials banks. And many of you know that buildings as materials banks is a popular circular economy solution or proposed solution. So I'm conscious of time here. I know we're up to 20 minutes, but it was just interesting that Chris has also worked on a multi-life cycle modular building configurator. And I think that's interesting because it lets us explore the operating and environmental impact and capital costs of different designs. And then the configurator can also drive the supply chain. So I would like to move on to the next slide. What do I need to do here? Okay, there we go. Okay, So, see, we've come up to 20 minutes, and I was told 20 minutes was our time limit. So, in summary, I shared some examples of construction and deconstruction research and how they can help enable a circular economy in the built environment. I hope it was interesting. I hope it was not too scattered, and I'm looking forward to questions from the audience. Thank you. So.
Thank you, Professor Hart, for your nice presentation. Very fruitful sharing for us. Now, may I also invite our moderators, Dr. Siu, for holding the Q&A session for us, please.
Yes, and I just realized I was supposed to stop sharing, so hang on, sorry about that. Okay.
Thank you, Professor Hart. Thank you for your great presentation. It seems that it is quite late night in Waterloo because
Yes.
the room is quite dark.
Yes, yes. It's dark and cold outside.
Yeah. Okay. While waiting for the audience the question, let me ask one question first. It seems that you introduced the various studies. Firstly focusing on the on-site measurement and some ergonomic analysis, and the later part. Actually, I'm very impressed on the research on the deconstruction, especially the disassembly, because in Hong Kong we are also adopting some modular construction. Actually, we call it as a modular integrated construction. But it seems that the many contractors and the engineers are not fully considering the how to demolish, like how to do the assembly work after the finish of the end of the life cycle of the building. So, but I strongly believe that for the more effective disassembly, maybe design of the structure should be totally changed. So it could lead to some increase of the initial cost, I guess. So could you briefly explain how it would increase the initial cost?
Yeah, for sure. I agree with everything you said, and that is the trade-off. That if you want it to be possible to disassemble, typically the connections cost more, and actually even sometimes the construction cost, because of the labor involved, costs more. So we would have to make a social economic decision that future environmental impacts had some value to us today, and we would have to also put some dollar value on externalities, energy, carbon impacts that we don't now. But if we put some value on those externalities and we thought about a social rate of return on investment, so a very low interest rate, then if we discount those future benefits and future costs, and it might look attractive. That said, most developers plan on flipping their development as soon as they build it, or very soon after. At least in Canada, most of the developers have no interest in cost beyond the date when they have sold the last unit and turned it over. They leave the condominium association to deal with operating costs. So it's a big problem. Yeah.
Yeah. Okay. Thank you for your answer. Okay. Okay. Actually, also during your presentation, I saw very interesting the human-robot interaction study, the use of the self-leveling palette. Probably you remember it's been a while, because when I visited Waterloo like 5 or 6 years ago, you were working on the masonry work. It seems that you developed some self-leveling palette. So how's the applicability of this palette at the construction site? Because it should be movable, right? During the progress.
Yeah, that's a good question. And I know you're an expert in this area. You've done a lot of work in this area. And it's interesting. We did not develop the palette. It's a very, very simple solution that you can buy for factories. What we are doing with our partners is making the palette so that it's more mobile. because you identified one of the problems. These current designs tend to be heavy and they tend to be used on a warehouse floor. But we need a design that's lighter. And I think it's quite possible. I don't think it's any harder to build a light, mobile, self-leveling pallet than it would be to do anything else in a masonry construction environment. I mean, we have to move the concrete masonry units also, and they're even heavier. So I think it's feasible, but not always.
Okay, I see.
Yeah, it's a really simple solution. We were just showing that it's so simple. We and our industry partners are really excited about it, and it's very strange that nobody ever thought of using these before in Canada. Maybe they use them elsewhere in the world.
Yeah, definitely. I strongly believe that simple is the best. Yeah.
Yeah. It's
okay. If we it seems that we don't have any other questions from the audience, so that we need to finish right now. Okay, thank you. I do appreciate your excellent and valuable presentation, and I hope to see you in person soon.
You too. I thank you. Thank you for inviting me, and I appreciate meeting everybody virtually. Okay. Take care. Good luck.
Bye. Bye.
Bye.
Okay. Thank you, Professor Hart and Dr. So. Thanks for your sharing and discussion. Let's move to the next presentation. Now, may I invite Professor Mohammed Al-Hossein to give the presentation on the topic of strategy for efficient modular and off-site construction practice. Professor Al-Hossein is a professor in Department of Civil and Environmental Engineering, School of Construction Engineering at the University of Arbor. He is also an SERC Industrial Research Chair in the Industrialization of Building Construction and a Director of Nursery School of Building Science and Engineering. He is a highly sought research in the area of building information modeling, in manufacturing, construction process, and optimization. Dr. Al-Hossein research has been published in over 200 scientific journal articles and conference proceedings. Let's welcome Professor Al-Hossein, please.
Ladies and gentlemen, good morning. I would like to take this opportunity to thank the organizers for inviting me to be part of this symposium. Allow me to share my screen for this presentation. My name is Mohammed Al-Hossein. I am a professor at the University of Alberta. My focus research on modular and off-site construction. I take this presentation into a different level, how modular got affected by the COVID-19 pandemic, and what measures to be taken to protect the workers during this time. If you all know how manufacturing or fabrication is really human-centric. People move in and out. Sometimes we jump quickly to make a volumetric box. We'll allow the people to move with stations. The focus has been primarily on efficiency, reduce the cost and the footprint of the factory when it comes to measuring and distributing the work between workers. Little been attention to something called COVID, which came this year to the surprise. So 4 items I would like to share with you, or areas of research. One is digitization. I am aware of your program has speakers more qualified than me when it comes to digitization. So, but for me, is a 3D model which I have. I can front load it with specific information that I can use for the factory. Instead of having people to go between each other and provide some instructions, share documentations, drawings, this all could be done by virtue of screens and communications from the central hub into the production line or into the floor where it's needed. Robotics is another area which is emerging more into construction nowadays, and demand for robotics become more evident in the last few years. I would like also to share with you how VR, virtual reality, could be utilized to help this industry. And then also I would like to share with you some change of the process instead of the change of thinking how we can manufacture or fabricate fabricate what you need when it comes to the modular industry. Digitization is the concept which is widely used in other industries. In construction, less of that. Modular industry has the opportunity to use it, but is not really being fully utilized the way it should be. As I said earlier, communication between workers from superintendent to worker, all that could be done through digital, within the digital environment. I'll give you an example here. As a foreman, instead of walking around and talking to the people, he may have a platform in front of him, and that platform shows the people, the stations, and the actions. He can provide instructions for some of the people to change the locations where they are and go to perform tasks. For example, this welder here is being asked by communication device to change what he does, interrupt what he does, because he's qualified to do some certain operations. In this particular situation, delivery of material using the forklift, and then he can go back. So all this be captured. Again, the effect of that in his production could be all digitized and seen by the foreman who did initiate the action to start with. Robotics and automation are degrees. The highest degree of that, which is the multi-degrees of freedom of robotic arm that could perform tasks. But you can do a lot with a single dimension, moving in horizontal line, or moving in vertical, that will be the second dimension. If the material move into a different dimension, all of a sudden you get really 3 degrees of freedom or movement between the items you put in the station and the work is performed. Yes, robotic arm has the potential to do a lot of what the human work in, articulations into welding and cutting and cleaning, which is really could be widely used. I look at it how human can put together pieces that form a wall, for example, in a wood frame. It might need more than one person to do this operation. The same thing, you can really apply multiple robotics. Whatever the human can do, the robotic, some of these tasks could be done by robotic or multi-robotic or robotics applications, either with the robotic alone or robotic and human between different stations. So the interaction here will demand a new level of interaction and new level of planning and scheduling for these to operate. Can robotic do tasks such as electrical wiring? Can it really sawed into the wall, whatever is needed in terms of wiring and plumbing, and perform all the tasks? Perhaps yes, with a little bit of a degree of intelligence in the system. Robotic can really perform most of the tasks that we see them today done by a human. So this operation is simple, but again, robotic can do. Now I move to what I have done. I've been working on designing machines, building these machines, but the entire concept was based on efficiency, reliability, consistency in terms of performing of the task with relative variations in the amount of time it takes to do. Now, if I would add a human to that machine, how that will be different. So with my design criteria change, given that I need to bring one or more human to interact with the machines. So how that will change, that change will affect my ways of thinking. Can this operation you see here be done by one single person rather than two? Can I separate the workers? And then can I quantify the risk I am adding with this machine when it comes to pandemics such as COVID and the effect of that on the workers on the factory? So this is what you see here. The machine is being built, tested, to see now if I can look back to see how I could have done it better when it comes to accommodating the need for isolating the people. Can I really change the sequence of putting the pieces together so then the machine will be used by like interaction between the human and machine will be higher with single human rather than multiple human to do the operations. So that's a little bit of a new demand for how we can really make the factory working all the time rather than allowing the pandemic to stop the operation within the factory environment. Can I have, as I mentioned earlier, so instead of having two people, can I change the sequence of the operation that one person can bring these pieces. I can count on gravity to bring the material rather than having two people to carry it. So the machine can also somehow, we can add a little bit of dimension to see whether interaction between the human and machine with articulations, whether it could be welding these components. This is light gauge steel, or bolting the system together. So if I look at that from the wood perspective, the same thing, movement of people, we have studied it in terms of ergonomics, efficiency, but now I want to look at it whether I can really reduce the amount of interaction between people by adding a simple machine. What you see here in this place, really a new concept of a machine. We put it where it's needed, and the human can interact by himself with the machine. Key for me is the material that is delivered in a way that human capacity can lift it and put it together without having a need for more than one person to do the operation. The same goes into larger components. So can I use the gravity, deliver the material, separate the human if I need to, into a distance that is allowed by the expert who's telling us how far we should be apart from each other. What can we do, how we can change the machine and the sequence of operation to accommodate such a demand and such a need. So if you can see, the machine was designed for one purpose, now have to be redesigned to accommodate a new demand, which is, I call it here, COVID restrictions on the manufacturing process. Can we add some of the items, or some of the work could be done with the robotic entirely? If you see here, people have to lift. These are, yes, they are made, which is drywall and sheathing are made for the size of human to be able to carry them. But again, there are two people needed, one to hold and one to screw. Can we really add a technology that will aid this particular operation when it comes to increase the number of the risk of COVID? If I look at the adding different degrees of automation, this is the machine which was designed here in my lab. And we really focus primarily on how to perform the machine to provide consistency, to provide accuracy, to provide speed with limited amount, with least amount of space. But if I add a human on this machine, which you see exactly the same machine, if I add a human to operate this machine, what that means. All of a sudden, I have to see whether I need one, it must be more than one. Can I space them in a way that they can work? Can I change the operations? So you notice here, one individual will work alone and perhaps will operate the machines, given that I am within the allowable speed and the allowable consistency in the work. So this machine now has a little bit of improvement in its design. Little, really, did not require lots of changes. Just I want to see how the human in the virtual world, how the human will be interacting in this case, and whether I can have a measure or a metric to measure the mitigation of risk when it comes to epidemic-related restrictions, human interaction with humans or human with the machine. So that has been done. If you look at what you see here today, this human, yes, I was measuring primarily the efficiency, the amount of time it takes, and the consistency. Now we're looking at how much interaction and how little, if possible, interaction between people to people. The focus will be primarily on machine to human, and if possible, machine to machine, rather than so minimize the impact of interaction in the factory. So this way, this factory could remain open with providing the protocol for the government for their measurement they take to reduce the impact of. Look at this situation here. So can we change the way this operation could be done? If you see, there is a lot of people. We did it on purpose because we need to match the speed of the production, but that could be changed to see if we can really allow a robotic arm versus just these humans. So every task could be studied, and then the metric that will measure here the amount of interaction, and we call it the risk factor or risk variable that comes out of this operation. If I go to manufacturing, this is for hospital mechanical system in a hospital. So can we design, we have designed all this in the past for efficiency, ergonomics, and minimize the number of movements, waste, lean concept. But now I need to look at it, how much interaction I am exposing the workers to each other. When it comes, if you look at these people, they have to work much closer to each other. So what can we do? Can we change the sequence of operation? Can we change the tools they use? Can we add a new sub-assemblies? Some of these components could be sub-assembled in a more controlled environment. So yes, we focus primarily on cutting these pieces to fit, because we use the place as a prefabrication or assembly of prefabricated components. The tools has to be designed in a way that eliminate or minimize the interaction between human. Yes, it will still gain the efficiency we're looking for. If I take this into this side, so how I can really move the people around and minimize the interaction. I focus my philosophy on fixing the people, fixing the tools, but that means I have to put people together in one location. So in this particular operation, the modules, which will be fitted in the corridor of a hospital, they come, people sitting and work comes to them. So the focus primarily have been on ergonomics efficiency, but now I can look at it from different angle, how much risk I have with these operations on these workers. What can I do to change? Is it add a tool or add a sequence of operation? If you look here, yes, we clustered the people together because there's lots of operation that has to be done in a very short period of time. And the way we did it, that will add a person for specific tasks. So all will be done within the time waiting from one module to another module to arrive. And this case, yes, has a little bit higher risk. So what can I do? Can I relax the schedule? Can I change the operation? Can I have a little bit less of some of these operations that require way more human for a longer period of time? Can I shorten that by adding a technology, adding a tool, or changing the way we really hang these devices in the corridor of the hospital? If I look at the entire factory, so I can really have localize my criteria and localize the measurement. I measure when it comes specifically now to COVID-19 risk, i.e. the risk of people interacting to each other, and what can I do to change? Do these people need to do this operation? Can I add a sucking system to take it? We can see here these people have to interact with each other all the time. So what can be done? Can we add a different arm? Can we add a different techniques to automate? So in this case, we can really have a new metric to measure. Yes, we measure the efficiency, we measure the consistency, we measure the reliability. Now we have to measure, in addition to that, the added risk when it comes to keeping this factory open. I look at another dimension, window manufacturing. You can see the windows made of components. These components are cut from raw material in the same factory. And this operation here, installing hardware. So if I look at the installation of hardware, it takes a lot of space, and then the space also filled with people. So we propose additional systems. Can we change the tables the way they're done? Can we add a screen that provides you with the information rather than going to look for information? I can have really a record of inventory, how much pieces of hardware that is needed, missing. Instead of having the people to go interact, this could be done all through a screen that could provide this information. We can really change the layout that will open up the space between the tables to reduce the interaction. We look at it from an ergonomic perspective because you have to put within the side view rather than having to look for things around and maybe punch with each other. So we look at these dimensions and we qualify or quantify the amount of risk that these people, and then we put what they call this configuration space of human. The human need to move around and within the space that allow them to do the operations without being interacted with others. The only interaction will be with more machinery. So I move that to instead of having the box being welded in advance, how I can really make it in a linear production in 1D rather than 2D, the way you see it in the top screen. The bottom screen is linear. This is in my lab. So the student here, they start adding the hardware before you go to welding. This was a no-no until the company not only saw the value of that in the ergonomics, is the speed and reduction of the space in the factory. So basically, this production, which is on a table, allow me to have people working within the closed environment. A very simple operation, did not add a lot of cost, but also it added a huge amount of efficiency and reduced the space. This space, which used to be in the past, now we need less than a quarter of that space to perform the same operation was performed in the past. So I'm moving the operation from 2D operations into linear as much as possible before I really need to go. So all this hardware now could be installed, maybe 90% of it could be installed before welding operations that happened. The second task I would like to share with you, the effect of COVID on the sales. So the builders complained that people could not go and see, to visit and to see show homes, to be able to choose. For a period of 2 months, really, that will be March and April last year, very little sale has happened in the market, because one of the reasons was people could not go and choose. But again, when I look at it, that's create an opportunity. So how I can use the virtual reality instead of people going to choose, what the people want to choose is really finishing from the wall in. They care less little bit on what the structure, because they know that meets the building code, meet the requirements by laws. But from inside, it's the choice that the human have to make, or the home builder. But the choices are so much to choose from. Then they had to travel around the city from one place to another to see what kind of sinks that's available, what kind of cabinets are available, what kind of choices. It's really a huge amount of interaction, and these people have to travel. If those all close, then the potential for sale will be reduced. So I'll give you for kitchen cabinet, what the people look at. So do they look at just the look, the doorknob? But again, I need to go inside the functionality of that cabinet. What goes in the cabinet in that kitchen? So we start to study that in much more depth, and based on that, we can make the people use design from inside out rather than designing the cabinet from just for the look of it. Even if you look at the electronics which you choose, whether the fridge, the stove, there's so many variations of varieties. What are the criteria that will govern your choices? Is it the cost? Is it the look? Is it the shape? What kind of appliances you really need as a family, which is really sometimes that's a challenge some people have. If I go to choose the faucets and the sinks, and there's so many variations, so education become an important factor to make the homeowner making a decision to buy and to choose to make the choices for his home. So what we're trying to use the virtual reality for that concept, so that people can design the kitchen and the bathroom and the interior design of the house in the virtual world, but by capturing the needs. So what are the needs? Is it the family-based needs? Is it why the people choose what they choose? Is it really triggered by culture? Is it triggered by age? Is it triggered by level of income, level of education? So if we can capture all this information, we can really use the machine learning. And then with the next couple comes, or a company or a family comes, if they answer a few questions about who they are and where they come from and so on and so forth, they can really give them people from that category, this is what they choose. So basically we can really make them, give them an education, and then they can make an educated, informed decision on what they need to do, because what the home builders discovered that this is the hardest part when it's selling a home, what they need, how they can choose what they need at the end of the day. And it's really, really tough moment and short period of time. And I would like to conclude my presentation by the look of the factory. So this is what you see here is the factory I work with. This is in Brazil. So I look around, and yes, there's everything is wooden and tarp in the bottom, and there's lots of safety requirements, space. But I said, well, listen, why don't we lift it up? If you look at the amount of time workers spend in the factory, they can work 8 hours or 10 hours shift. This is majority of their time is in this factory. How about we can really add some lights, change the colors, the colors of the flooring, and all of a sudden the factory took that, and this was done in April during the pandemic. Then if you look at the factory, what was before and what is the factory today, it really changed the attitude of the workers. Little, did not cost much to do, but it was really something the factory feel proud of. So what to summarize my presentation, I focus on how I can add automation to the manufacturing process to reduce the interaction between human. I presented primarily 4 areas, which is digitizations, robotics, virtual reality, and change the process by linearity or linear production of the system. This is the factory, which is Lafayette in Brazil, which I really feel proud of what we did. With this, I conclude my presentation. I welcome your question. Thank you.
Thank you, Professor Host, for your nice presentation. It's a very interesting topic to improve the construction productivity. Now, I also invited our moderator, Dr. Steele, for holding the Q&A section for us. Dr. Steele and Professor Host, please.
Thank you.
Professor, thank you for your great presentation. According to your presentation, it seems like these days the assembly modular shop is like a very high-tech manufacturing assembly line. I can see some automation and the robotics technology there. But I know also you have been working with the professors in Hong Kong for the for the modular construction as well, and probably you know the differences between the modular construction design in the North America and the Asian countries. Even though in North America you are using some wood construction a lot, but in Asian country mostly we are using just concrete and steel, even for the modular construction. Do you think some automation and the robotics technology you introduced in the slide can be applicable to some modular construction that are mainly using the concrete and steel?
Yes, I believe knowing what is happening in mainland China, there's lots of automation on the precast, and China produces, even most of the Asian countries, Singapore, Hong Kong, they produce way more precast than any other place. So it's automation is happening, and I've visited quite a few factories in China, which really highly automated, and some of it really, the machine itself is a China-made product. So it's really compatible to what I have seen in other places. So the answer is yes, it already exists. The technology, and it is really at its very high quality too.
Yeah. Okay. I just briefly mentioned before, in Hong Kong we are just the beginning stage to adopt some modular integrated construction. Actually, the Hong Kong government are facilitating the use of the modular construction in Hong Kong as well. But it seems like the use of the modular construction in the big cities like Hong Kong could have some limitation. So could you because you are one of the leading scholars in the modular construction area, so I'd like to ask this question, whether there would be some remaining challenges to adopt some modular construction in the big cities?
Well, the main challenge is really the size of the modules, and that's basically the main challenge. But that challenge has been overcome in many places, including Europe. I have witnessed the work has been done in one of the companies in Spain. So they can send volumetric models, which is exactly the size of the truck. So you can really put it in a tray on a truck bed, and it fits the way the truck can move between in the streets in the city. These models are as much. So the key is the model themselves are unique, but then the facade you bring into all kind of finish material you can clad it in. I wish maybe I should have really done my presentation focus on precast concrete, but I thought I would put it a little bit more into the epidemic, which is so yes, there should not be any challenge. Yes, the streets are small, and the streets also narrow in Europe, in Spain, in France, in Italy, even in all European cities are no different. The streets are narrow, But again, as long as there is a truck can drive through this street, you can also bring that model. The challenge is you have to make these models fit that size.
Okay, okay. Thank you for your clear answers. Okay, okay. We are still waiting for the question from the audience. Okay, if then I'd like to give one more questions. Okay. By the way, because to make the modular constraint more economical, maybe we may need to build some more taller modular building, right? So if then, do you think because I'm not that much familiar with this area, so that I'm wondering whether the taller building by using the modular construction would be possible, like a 30 or 40 stories of building.
Perhaps that's where it comes to the lifting capacity of the crane. But there are some cranes nowadays really with really high capacity. I have seen a couple of cranes now coming to the market, which is tower cranes. They can lift 120, 180 ton, which is metric ton. And I'm hearing that the industry is really preparing for doubling that size. So as long as there is a demand, the industry will react. There is quite a few crane companies in China. They produce heavy mobile cranes. The mobile cranes need a lot of space, so they're really difficult to put in cities. Where tower crane is the one, so if you go 40 stories and more, what you just mentioned, then you will increase the capacity of the crane. So 40 stories is happening. UK has already did a few buildings in 40 story or higher, and the cranes are coming bigger and bigger nowadays.
Okay, okay, I see. Thank you for your answer. So for the sake of time, we need to finish your presentation now. Okay, I do appreciate your presentation.
Thank you very much. It was nice talking to you, and good luck with the conference.
Okay, thank you.
Thank you. Thanks.
Thank you, Professor Ahout and Dr. Sid for the sharing. Next, let's move to the last presentation in the morning session. Now, I invite Professor Kincho Lau to give the presentation on the topic of opportunity and application of ICT, civil and building energy. Professor Kincho Lau is a professor of civil and environmental engineering at Stanford University. Professor Lau's research interests focus on the computational and information science engineering. His research has dealt with various aspects of high-performance computing, sensing, monitoring, and control of engineering systems, legal and engineering informatics, smart manufacturing, web servers, and clouds, and internet computing. Professor Lau was elected distinguished member of ASCE 2017, fellow of ASFE in 2017, life member of ASCE in 2018, and senior member of IEEE in 2019. Let's welcome Professor Lau, please.
Thank you. I already share my screen. Hello?
Yeah, we can hear you. Can start.
I already shared my screen. You want me to do it again? I don't see the screen. Do I see the screen?
Yeah, you can share the screen, and now it's okay.
All right. Okay, thank you. Thank you, everybody. Good evening, good night, or good morning, whatever you are. So what I would like to share with you today is about some of the work that we did on ICT related to civil engineering. But I also want to really discuss the opportunities. My main talk will primarily about very general about ICT in our industries. So the conference title is about innovations and productions. So we'll see how it goes. So first, the acknowledgement. I would like to thank Professor Jack Chang to inviting me, and also the conference organizers organizing this meeting. Occasionally, I do get funding from the U.S. National Science Foundations. I also have funding
from time to time from the Advanced Manufacturing Program from NIST, and also from time to time with funding from the Stanford SciFi. As always, the work are primarily done by my students, so I would like to acknowledge their contributions. And I'm the one who giving the talk here. But I would like to emphasizing the disclaimer that whatever I present here, stay here, and do not necessarily reflect the view of the agency and the collaborator. And also that if I mention any commercial system or any methodology discussed here, they're not necessarily the best for the purpose. That is the disclaimer that I need to put up for the funding source. So I came across an interesting article a couple of days ago, since now we all kind of stay at home, so I read magazines, and this is a interesting quote conclusion. The article written by a very well-known company, people working in very well-known company. And when I reading this conclusion paragraph, I feel kind of interesting. Basically, it's a AI can be used to advance through any decision point while automating tasks that are high volume, low value, so low value, and mostly repetitive. So I kind of find it interesting, but I think that is a general impressions that the industry has about automations in the industry and AI in general applications. May not be in other industry, but I think in our industry, it's kind of common view on computing in our industry. And again, McKinsey said the same thing, actually. This is a report from McKinsey Global Institute. There are a lot of opportunity there to improve productivity in constructions. But it basically said we do have a very long record of very poor productivities. And I'm pretty sure many of you have seen this article before. So one of the items that they do put out is that ICT could have a lot of opportunity to improve the productivity in the civil and construction industry. So but when you talk about ICT in technology, it's actually extremely broad. I mean, we can see almost any enabling technology can be applied to our world. Of course, I mean, everybody knows building information modeling, computer visions, and 3D printing, all the way to Internet of Everything these days, and AI, of course. I mean, Industry 4.0, Society 5.0. Blockchain, cyber physical systems. So we have a lot of these words that running around. It's kind of interesting to see how many technology that can be applied, okay, so to our industry. So, but the basic theme that I would like to convey today is really we need to bring all this technology to interoperable and apply them efficiently. I think that is the main thing that that we need to deal with such a broad spectrum of technology that we have. So this talk, I'm going to go through a lot of buzzwords. These buzzwords, information modeling all the way to machine learning that we're probably going to hear over and over in this conference by many people and a lot of presentations that is going to cover a lot of this material is actually will be much more appropriate and better than what I'm going to talk about. Application-wise in our industry that we probably can apply them to supply chain, modular constructions. My work is mainly infrastructure monitoring and also do natural hazard mitigation type work and robot navigations. So I'm going to talk about how to bring some of this technology, merge them together with application example to share with you what generally that technology can be applied to industry. And then I'm going to first summarizing the trends and give a couple of general remarks. So in the next 20 minutes or so, I hope to share with you some of the previous work that we have done. So back into the 80s, and we started to moving from 2D CAD drafting CAD to 3D modeling. And then we eventually moving to object CAD systems. In fact, the word objects at Stanford, when I was assistant professor, we got pushed by Professor Paul Taiso at SAIFI to basically say, we gotta put together object system instead of looking at lines in a CAD system. But what it comes down to is that the objects, object-oriented programming, they have attributes, they have methods. So trying to mimicking the object-oriented programming paradigm and into the object CAD environments that including project information, that bring to a lot of interesting development related to product and process modeling. Of course, beyond object CAD is what we now know as building information modeling. And again, the evangelist, Professor Paul Taiso, and the late Professor Chuck Giesman, very unfortunately, he just recently passed away, are the evangelists of the building information modeling to our industry for the past 20 years. I mean, they are the one that really pushing very hard for our industry to adopt and developing a lot of technology to help adopting such technology. Fundamentally, building information modeling can help us is to enriching the semantic of the model and also using standard syntax that we can then start to do data interoperability among applications. So just a quick example that one can doing objects, they started talking about stairs, or talking about a different type of objects of a building, but at least one thing that we can really easily see from the advantage of the building information model is we can overlay different discipline into the model, and then we can do checking on clashes of objects. We can then go through the entire project and see how that may work out. And of course, I mean, the building information modeling had gone really applied to many applications now, from asset management to supply chain management. So one thing interesting is what's appear on the screen is not on the other screen. Or you have significant delay. So I just keep talking. So as I said, the building information modeling can apply to the industry quite broadly. Of course, the other technology also emerging in the mid-90s is the internet, particularly the web browsers environment. And what is interesting to me is that the internet can also be used as a communication platform. So we can actually using the internet as a means to connect applications. So that's what called service-oriented architectures. So very early on in the mid-90s that we start, one of our PhD students, Dr. Chuck Hans, has proposing how to utilizing the internet as a way to build collaborative tools. So we're not just using the internet, but we also want to be able to translating the model. So we adopting the IFC product model very early on. This is probably version 0.1 at that time. So we basically can take the CAD package and then move it to our own CAD programs. And then we can developing software in a very modular way, such that we can connecting to a code checker applications or accessibility motion planner applications. So what it does is then using the internet as a communication infrastructure, using product model as the way that we can interoperable from one software to another software. So as a way that we think that is at that time how the services are being used in a distributed fashions for the future. So to move on a little bit, then we can see that we can now actually can drag and drop products from one package to another package, and then we can actually design on write on lines and then putting objects into a design task. And then we can summarizing what we use, and then we can come up with the procurement and all the way to do the workflow and supply chains. So that's the work by Professor Jack Chang when he was a student at Stanford University. So the idea is that again, utilizing the internet as an enabling technology to help collaboration, workflow, and helping the development of supply chain. So supply chains, a lot of people thought in the industry is moving one material from one site to another site to another site. And more that this material flow process, we still need them, but a lot of work is being done on the back end as an information flow. So the key is that since that now we have the internet and we can now also have information system, a lot of things can be done at the back end before they actually go into the producers, the fabricator, and eventually go to your erections on the in the construction sites. So the transformations that because the information ICT technology is the supply chain become a information problem. And as we start to see what is going on right now in the modular construction of PFAB type constructions, what we now seeing is seeing more and more on the logistics and supply chain become a very important part of the development. So again, that turns into the ideas that information is the key on the in the modular constructions that we see in the future. So the notion is that information technology can actually help and supporting a lot of construction process very efficiently. The other type of work that I have been interested in during the same era, the late 90s and early 2000s, is the emerging on wireless technologies that we can put together miniature size sensors, and we can put it into structures. So we can mounting sensor on a, say, for example, a bridge, doing infrastructure monitoring. So with the sensors on the bridge, then we can then measure the time series data like vibration data. Then we can look at mode shape. We can look at a lot of natural frequencies and other type of structural parameters of structures that we deal with, and then we can merge it back to the digital model as you wish. So sensors then become a very popular thing in this day. In fact, this is what people generally know, Internet of Things, and basically you have sensors that can attach to almost any artifacts, and even including people and environments, and measure a lot of things. But one of the problem is that we started to have a lot of data. So all the sensors all over the place, and we're going to collecting a lot of data. Then two questions is how we're going to store them, and then how we're going to use it. So those are the two main themes that we need to focus on. First of all, the data set is very large. I mean, that's why we may need to utilizing cloud services as a way to help out how to scale up the storage problem. And the other question is how we're going to use those data when we need it, and what kind of application we can use it for. So we had a project that I worked with Professor Lynch at University of Michigan, is looking at how to put together a framework on infrastructure monitoring using with big data, and also participated by Professor Hong Zhang from KAIST. So fundamentally, what we do is that we're looking at the cloud surface as a way to help us to scale the problem. We also trying to looking at what type of data analytics that we can utilize the data we collect. But one of the things that I do also in this project is trying to put an information model. And so that will give me a way to define a database properly to store the sensor data. So the infrastructure information model that we built, that is, I have not found a sufficient detailed bridge information model for monitoring purposes. So we started to look around the what do we really need? So we need a software simulator that allow us to simulate the response of the structures. And we have a lot of sensors that we mounted on the bridge. So I utilize the sensor ML as the base to build a information model. So in a way that I'm trying to merge the engineering software and also the standard that people might use for sensors to merge them together for a bridge information model that we can utilize for infrastructure monitoring applications. So with the bridge information model, then we can directly map it to a NoSQL database. We're using Cassandra database. It's good for semi-structured and unstructured data. So we can utilizing the database schema and directly we mapping the bridge information model onto the NoSQL database. And then we push it to Microsoft Azure and the cloud, and then we run it a distributed distributed database to store the data and then also access the data. So we try to collecting sensor information. We have a backend bridge model, and we try to collecting traffic information and to build up the database that we can utilize for infrastructure monitoring. So we instrumenting the a highway corridor in Michigan. So this is I-275 highway corridor. Basically, we have 4 stations that we are trying to measure the information. So the first one is that when a truck comes in, we're trying to looking at the traffic right in the traffic using the traffic camera, and then we putting sensors on the telegraph bridge, and then we also put a sensor on the Newburgh Road Bridge. So they have strain gauges, accelerometers, and other type of sensors that we need to capture the response of the structures. And at the far end, that we also have a weight in motion stations that you're trying to basically measure the weight of the truck as they're going through. All we're interested in is truckload. So because those are the most stringent loading that typically on the bridges. So this is a 15 miles corridor that we instrumented with camera and sensors. So of course, with the data mounted on the cloud, then we can easily using Cassandra query language to carry the traffic and informations, and also carry the sensor informations, and then you can see exactly the vibration measurement compared with as the truck is going through the bridge that we measuring the vibration data. And also very easy now, they're building web the apps that can run on the iPhone, so we can easily build apps to looking at the sensor, know exactly where the location of the sensors. At the same time, we can actually go to Google Map and looking at the bridge, and then we also can looking at the record the sensor information. So going through the cloud surface then will really help us out to build a lot of mobile and web service applications. So now we have the physical model that we capture measurement. We also had a backend digital model that we can run simulations. Then we can now comparing what we measure with what we actually can simulate from the digital model. And for example, using the measured sensor data, and we can compare with the same vehicle that kind of going through in the simulation program, then we can looking at compare the static response versus the dynamic response. And this important parameters is called dynamic amplifications, factor that due to the dynamic load on the traveling truck going through the bridge. So we can now using the cyber physical system to that instrumented with sensors with the back end of digital simulations, then we can compare what is being measured and what is being simulated. And one of the things that I personally believe, many people might not agree, that I do believe that digital twin model should reflect the nature, but the level of what is intended to support. I see a lot of very sophisticated digital model is very complex, and that could have a information overflow issues. As a researcher, I try to always say make the model as simple as possible, but no simpler. So one of the things that my thought is that when we build digital twin model, we're trying to look at the purpose of what we're trying to build. At the same time, trying to make the model simple, because simulations on model is not that, it could be sometimes very computationally intensive. So that's just my experience on in this particular project on how to putting a digital simulation model at the same time on collecting data and how to do real-time comparisons. So this is a corridor, 15 miles corridor that is actually in a way is an interconnecting system, because when the truck coming in from one end, then the truck will go through the two bridges, and then we will go through the weighing motion stations. So we want to capture the data as a truck going through, and we want to capture the same truck as they're going through the monitoring system at the same truck that we're going through the weighing motion system. Of course, the technology now we can do that with machine learning, that we can easily identify capturing the truck as they go through the stations. And then we can scoring the truck as it's going through the bridges. And then we can also scoring the truck as it passing the weighing motion stations. So what it end up, then we can find out exactly the response of the bridges, from this traveling truck vehicle. And we can also measure the weight of the vehicle, as well as the approximating or estimating the speed of the vehicle as they go through the bridge. So we can now basically have input and output measurement of a physical system. And this is important because most of the system identifications primarily can deal with output measurements, which is not necessarily as accurate as we have a both input and output measurements. And also can help us to really identify the low rating system, because we have the load information. We can also have the bridge response information that we can actually do very good comparisons on the two things. So machine learning can actually be very helpful for infrastructure monitoring applications. And of course, I mean, in the vision-based machine learning, then we can also capturing the images of the bridges and be able to identify damage as we go. So this is one example, a contest that being carried out by the Pacific Earthquake Engineering Research Centers. And this is a couple years old, but on the other hand, you can see the accuracy is actually not too poor. So we can actually applying machine learning technology now to do damage identification and also do damage segmentations. So we can identify the structure, material, and many information that we can do computer vision-based machine learning. So one of the projects that we have at the SIM Center, Center for Computational Modeling and Simulations, they did a rapid screening on soft story structures. So in the Bay Area is an earthquake country, so we basically using Google Street View images, collecting those images, then we can train the model, and also at the same time identify the soft story with the classification being focused, interpreting where the software identify the particular soft story, or giving a particular image that people have. So the overall idea is looking at the all the soft story structure in the region. So again, this is a vision based, so we can only see in the look at the pictures and identify. So we can creating a probabilistic map on the soft story building in a particular city. When we talk about regional type things, then we need to start to build a regional inventory system. So a lot of time we can collect a lot of those information from public record, but they usually incomplete. So we can also then apply machine learning techniques to fill up some of the missing data in the regions, and then we can do hazard mitigation analysis. So once again, the basic information that we like to capture are the parcel information that we out from text accessor file, parcel text records, etc., but they are incomplete. So for example, a lot of hazards that we would like to find out what's the shape of the roof, and those the records do not say what the shape of the roof. Then we can use machine learning to take satellite images or street view images, and then go through developing a machine learning model. And given a particular building, then we can identify what type of roof shape they have. So the idea then, once we identify the basic building information for individual building, then we can then do hazard analysis of the entire region. So we can identify the damage state, or we can identify the potential mean loss due to particular natural hazards. Once again, you can see that some of the information that we actually identify through machine learning model, and some of them are out from the public building records. So again, then we can merging those informations and help out the regional hazard evaluation that people have. Of course, we can also apply machine learning to capture images and updating a building information model dynamically, and we try putting a robot going through, they identifying the objects, and then they can then put the object back to the building information model. And then why we interested in doing that is then we can now supporting robot navigations, in the sense that when the robot seeing some cones along the way, then they can utilizing the entire building information to go through some motion planning or reinforcement learning algorithms to rerouting the navigation path to the goal. So again, using machine learning and reinforcement learning, then we can actually updating the building information model at the same time, helping robot to navigate the area. So what you see in a lot of these applications that we actually trying to do is to utilizing multiple technology and interoperable with them. And I illustrating the application to buildings and also bridges, infrastructures, and also in the city or regional scale type problems. So just a couple remarks to close is we see the computational power is keep increasing. So one of the interesting things that the high performance computing, the top 500 project has shown is about 6 to 8 years, the top 500 computer will catch up with the top first computer. And then another 8 to 10 years, then they will, the laptop notebook will catching up with the top 500 computer. What then really means is about 14 or 15 to 20 years, then the your laptop computer will be just as fast as the top first computer that you will have today. So if you're looking at what's the current high performance computer, the Fukuoka from Fujitsu, now in the LeanPack run throughput is about 440 petaflop. In fact, they just reporting that for machine learning application, they can actually have 2 exaflops throughput using this high performance computer. And the NVIDIA, then the GPU now can support 5 petaflops as well. So think about that. They another 10, 15 years from now, then you might have a exaflop computer on your laptop. And that is extremely powerful. That is extremely, extremely powerful. Imagine your laptop can run exaflop in about 15 years. And then the other technology, of course, communication technology. Now we talk about 5G. You know, everybody excited about 5G. But in another 10 years, 6G is coming. And 6G is very interesting. It can have throughput a terabyte per second with the latencies in microseconds. So, and we are now actually, you know, every 10 years, then the communication network will keep improving. And this is really amazing communication technology is almost instant real time that we can do a lot of work. In fact, some people believe that autonomous vehicle will be very safe once we get the 6G technology. So again, we have, like everybody have talked about, we have a mobility system, we have robotics, but in the real world, actually the fastest moving to me is autonomous vehicles that we just read about Shenzhen's now have driverless robots that can now running around the city. And this is up and coming. In the next 2 through 3 years or 5 years, then we will see that fully driverless vehicles may be running around the streets that we have. And of course, the UAV has been around and people started using it for health monitoring applications. And so the mobility systems are now really emerging. So how about construction site? When are we going to see this interesting technology that can move into the construction environment? So I'm talking about this. I'm talking about now this real practical applications that emerging in the real world, not in the research laboratory. This is not real. This is a real world application, not in the research laboratory. So I'm challenging in the sense that the construction industry is take advantage of this mobility system. Maybe there is a lot of productivity and innovations that can come along. So another interesting technology that everybody excited about is called blockchain. So I kind of like this particular PBS summary about a particular application is in the art world. So you see that this is the art that they will have an RFID attached to the piece of art. So what helping from the RFID to the art is now you can register in the blockchain. So you can protect the artist IP and protecting authenticity of the particular art. And then finally, then we also, this particular piece of episode is also talk about using blockchain as a means to support collaborations. So we can see that you can now using maybe smart contracts or some things that you can build when people start collaborating on a particular project. Then what it really means to our industry is can our small medium enterprise in our industry can take advantage of the blockchain to help them to further their business and productivity and innovations developments. So a couple more words is beyond, we talk about smart city, we talk about digital connected city, but people started to have a lot of concern. The first one is economics, how you finance all these things. So putting sensors in entire city is not cheap. How are you going to finance all this? The other one that people have talked about already is the cybersecurity. So all the sensors, are they secure? What people haven't really thought much about is I call legacies. How are you going to do long-term maintenance on a lot of this technology? So this pandemic had taught us one interesting thing in the US. There was a push from some governors to say we need COBOL programmer. Yeah, COBOL programmer. Let me repeat, COBOL programmer. How many of you have heard about COBOL programming? But a lot of our legacy system in the government and also a lot of business are running COBOL. So this pandemic told us that basically, hey, those legacy systems are still alive. So we still need to maintain them. And that's what one of the issues that we have is think about the futures on the digitally connected society with a lot of software. What's the legacy? How are you going to maintain your software? And how are you going to maintain the privacy? And also, how are you democratizing the technology to the public? Do you trust the technology? People say blockchain, but do people even trust blockchain? So trust and distrust is a very important issue. One of the critical problems that we face in machine learning and a lot of the computational technology is the bias. So we see a lot of bias in our technology. The data are biased, algorithms are biased, and eventually technology is very biased. And these actually started to concerning a lot of people is the accessibility of technologies. Like in this pandemic, we also heard a lot of families do not have internet access. So, so we keep developing a lot of technology, but how about accessibility of the technology? And we might be creating more inequity when we're not careful about how to take concerns about the social, economic, and technological ideas that we are trying to build a more technological society in the future. So to summarize, then before 1980s, and we see a lot of interesting software development, finite element programming, critical power method, cost estimations, etc. I actually very fortunate to, I consider myself living in the golden era of computing. In the sense that I saw the development on information modeling, internet of things, cyber-physical system, and all the buzzwords that we've been talking about in my talk. But then the next is actually more interesting because now we have all this enabling technology that we can utilize. So we started to talking about vehicle to vehicle, vehicle to infrastructure, vehicle to everything, and all the way to now we talk about me to me, me to machine, me to infrastructures, and then we have me to everything. So I do believe that the next phase of the interesting innovative development is productivity through human-centered innovations. What we really mean is how to think about humans. How do humans work with the technology, or how the technology can help human to pursue, with the social consciousness and also other issues that we can think about. So how we can start to think about how to incorporate the technology with the human in not only in the loop, actually in the center. So those are the kind of things that I think will be the next phase on productivity development that I see, even in our construction industry. So with that, I thank you for your attention. Thank you for the invitations. And I welcome any comment and suggestions.
Thank you, Professor Lau. Thanks for your nice sharing and interesting presentation for us. To inspire us to more think innovation about IPC and machine learning into engineering and construction management. Now, may I also invite our moderators, Dr. Stu, for holding the Q&A session for us. Dr. Stu and Professor Lau, please.
Okay, Professor Lau, thank you so much for your very interesting presentation. Actually, I'm also working in the IT application in construction area, so that your presentation was very personally informative to me. And also, you have been working on this area for decades, so that your presentation was like some history of the IT application in construction. Unfortunately, we are actually, the conference has been a little bit delayed, so that maybe I can give you one quick question to wrap up this session. My question is, actually, in the last slide, you talk about the human-centered the innovation. So I strongly also believe that understanding the human and the interaction between the human and the IT system would be very important to improve the productivity, applicability, and the productivity of the IT system. But in this regard, do you think what kind of some human aspect would be the most important understanding this human-centered innovation?
So, but actually, I'm not really addressing the human machine interaction problem. It's not really just the interactions, how the human will be interacting with the machines. It's actually a broader perspective is when we're developing certain technology, we have to think about how does it affecting the human or the society in general. So when we put in sensors, that right now we put sensor, we don't really care about cybersecurity. A lot of time I do monitoring and I didn't, ignoring cybersecurity problems. So we should think about how to do that, and technology now putting in place. Privacy is a big issue. So those are human-centered issues that we need to think about. Don't think constructions doesn't have privacy issues. So we do have privacy issues because we're monitoring workers.
Yes.
Are those informations, how are you going to managing those informations? Those are privacy issues that you might need to concern. So what I'm getting at is not just say, oh, I know how to mimicking a human, using how the joints works and how to do different things. That's another back end that we need to concern about is how does it actually affecting. When you're mounting all the sensors in the construction site, you're actually making all these construction workers very anxious. They will have very high anxiety. If they know there are sensors, cameras all over the place, they will have very high anxiety.
Yes, yes, yeah.
So have you thought about the potential downfall with this type of technology that people might be thinking about? So those are the kind of issues to me. As we start to deploy more and more this technology, and they are so much cheaper and cheaper to deploy, we may want to think a little bit about that. Okay, of course, different society, different culture have different opinions on that. I mean, so but ultimately, those might have some interesting consequence. Okay. Smart city is a big topic and already bringing up a lot of issues about privacy, and some places don't care and some places care. So those are the kind of problem that I'm referring to, what I mean by human-centered innovation.
Yeah, thank you for your clear explanation. Personally, also, I don't like being monitored by some technology, even though I'm using technologies. So, okay, actually, we need to wrap this presentation, the keynote session. I do appreciate your valuable presentation. Okay, thank you.
Thank you very much. Have a good evening.
Thank you, Professor Lau and Dr. Steve. Thanks for your contribution for our conference. Ladies and gentlemen, this marks the end of the morning session. Our afternoon session will promptly start at 1:30 p.m. Please join the afternoon session at the same link here. Thank you.